C# is one of the most popular programming languages in use and continues to make programming easier and more fun with each new version. In this course, we'll dig deeper into some essential features of C#, like generic types, lambda expressions, language integrated query, and more. As we get started to explore part 2 of C# Essential Training, there are a couple things that you should know. First, I'm expecting that you've got some knowledge of programming languages in general. Maybe you've used another programming language, or you've tried them out, or you've got some basic programming knowledge. Also, as this is a part 2, I'm assuming that you've watched or know the content of C# Essential Training 1 and the Learning C# course on LinkedIn Learning, which was a prerequisite for that course. All of that's really going to help in this course for you to make sense of what we're talking about and really get the most out of it. In this course, I'm going to use Visual Studio 2022 on Windows. I'm going to be using C# 10 and .NET 6. If you're following along, the easiest way to do that is by using this setup. So if you have Visual Studio 2022 Community Edition, that should be fine. And you'll get C# 10 and .NET 6 with that. If you want to do something else, for example, if you're on a Mac, there are some other options. Visual Studio for Mac 2022 is in preview at the time of this recording, but you should be able to follow along in there for the core C# work that we're doing here. You could also use Visual Studio Code, which has support for C# and the ability to work with the .NET 6 compiler and C# 10. That said, I'd really only recommend this approach if you're very familiar with those tools already, or if you don't have another option because you are on Mac OS and you don't have the ability to use a Windows machine in the full Visual Studio. But again, I'll be doing things on Windows. It'll be very similar to what you do in Visual Studio for Mac with some slight UI differences. In Visual Studio Code, the C# itself, the editor will be very similar, but there'll be some shortcuts I take and things like that that will be different. In C# Essentials Part 1, we talked a lot about defining types. We defined those types with very specific plans in mind for how they'd be used. To start Part 2, I want to talk about generics, because this is a natural extension of defining types, but it allows them to be more flexible. Let's look at an example to help you understand why generics are important and why they were introduced into the C# language. Say I've got this method here called swap, and what I want to be able to do is have two objects or two references or variables, and I want to swap them. Pretty simple, nothing too complicated there. So I take the second object, I assign it to a variable called temp, and now I point second at first, and I point first at temp. As we're getting started, you may find some problems with this already, and hopefully we'll come to that. Let's say I just want to try this with some simple types. So I'll say x equals 5 and y equals 7. And those are just integers. And then I want to do console write line. So I might use my string interpolation. I can say x, and I'll put x there, and y, and we'll put y there. So we want to put out those values. And in between then, I want to call swap. And I want to just pass not x and 5, but x and y into that method. This seems like it should work. So if x is 5 and y is 7, when we swap these and write it out, it should say x is 7 and y is 5. But it doesn't. Now, if you watched C# Essentials Part 1, you know why. Because these are value types. And so when they go into this method and come back out of this method, they have different scope. We're actually copying values in there. You're thinking, let's use some reference types. Great. I have a person class that I've defined over here in my library. That library is referenced by my LinkedIn Essentials program. And it's just a simple class called person, first and last name and age, and an ID. And of course, you can grab these files from the exercise files and follow along. Now I've got some reference types. I should be able to come down and call swap on those. So I'll do swap P1, P2. And I want to swap those references. And now I can do a console write line. And now I can do something like this, where I'll say person 1, and we'll do P1 first name. And we'll just leave it at that. So if we swap these, we should then see that first name is going to be Amanda because we're swapping those two around. We'll run that again. Notice again, we get person 1 is Matt. Why is that? Same reason we saw before with the value types. So again, you're thinking, well, we'll add ref here because this is going to allow us not to just change the parts of the object, but actually change what they point to. Of course, we have to go back to the swap. We'll say ref here as well. And now we start running into some problems. We've got red squigglies. And if I go highlight that, it's going to tell me that it can't convert this from a ref of person to a ref of object. And the reason is a ref of object is very vague. That's kind of what we want here. We want this to be something that can point to anything. But that means I could pass in this person, but I could change it in the method to be an array or a date time or any other kind of object. And so the compiler's not going to allow me to do that. So we're a little bit foiled in our goal here. And this isn't actually the most ideal way to do this either. Even with our first example of swapping X and Y, the problem was we're taking integers and we're treating them as objects. Now C# allows you to do that, but it involves what's called boxing and unboxing. Any value type, ints, date times, can be treated as an object. That's a core principle of the language. But because they're treated differently in how the memory is allocated, it's an expensive operation. And this is where generics come in. What we want to be able to do is provide this swap method, allow you to use it with any type, but we don't want to use something like object. So what we can do is specify in our method this definition of a generic parameter called t, and that's a type parameter. So we're saying when you call the swap method, you're going to have to provide a type. And now, instead of object, we'll put t here. And then inside the method, we don't want to treat it as an object here. Again, we want to set that as t. So let's go back up here to our person, and we're just going to put that type, the person type in there, and pass those in and write that out. Now for this swap, we could come in and do an int. And now we can come in and say ref. And that's actually going to allow us, from the compiler's perspective, to do that. So what we'd expect if we swap the people is that P1 first name should now be Amanda, which was P2's first name, and X should be 7 and Y should be 5. So we should see person 1 Amanda print out, and then we should see X is 7, Y is 5. And that's in fact what we get. So that one little change, just being able to specify dynamically the type for our method, has made it much simpler for us to create a useful utility method or some sort of functionality. And then when we compile, it's the calling code that provides that type. So it's still going to get compiled in as that type. And we do know the type at compile time. So it can do all sorts of checks and other things that we would expect in our application. So these generic types, as we'll see, can be used not only on methods, but on interface definitions or class definitions as well. When you're working with C# and generic types, you're going to either be working with an actual generic type, meaning a class or record that has type parameters, or a generic method. So a generic method might be something like we've seen. I'm just going to paste in a little bit of code here. So this is just a string that represents some JSON, some JavaScript object notation. Pretty common format these days for serializing objects. And it just indicates that we've got an ID property, first name, last name, and age, which should look familiar. That's what our person class looks like. So now we might do something like var pj, or person from JSON, equal system.text.json. And we want to use what's called the JSON serializer. That's going to allow us to serialize and deserialize objects. And you'll notice the first option is a deserialized method that returns an object. But I know that the JSON I have represents a person, be deserialized into a person. It's going to choose the generic method. I can see here then that it has a type parameter. It just says t value. And I can also see that the return type is a nullable t value. So in here, I could say, I want this to be person. And then I'm going to pass it the JSON person text. And I should now have a person object that's been deserialized from that text. So we could do something like this. We write out to the console, say JSON person, and then we can do PJ, and I'll use this because it is a nullable person. So that helps me make sure that I avoid any null references. I'll do first name. Then I can come across and say is, and then we can do PJ question mark dot age. Got an extra semicolon there. So that's a generic method where you're going to give the type of the method, and that's generally going to map onto one or more parameters or the return type or both. We'll run this quick and we should see that JSON person come out as our output at the beginning. And there we see JSON person, Matt is 50. And if we look again, that's what we had in our text or our JSON. First name was Matt, age was 50. In C# Essentials Part 1, we actually worked with a generic type, albeit a little bit indirectly. We worked with nullable value types like this. What that shortcut was really referencing was a nullable of t, int. So we can write it like this. That's a generic type. What does that mean? Well, if we look at X now, we can see that there are properties on there called value, and it has a return type of int because that's the generic type parameter we provided. If we look at get value or default, that's going to return an int, again, because of the type parameter that we provided. It may be that what it's going to provide is 0 because that's the default for an int, or it's going to provide us with that value. Likewise, we take this now and we do a nullable of date time. We'll call it maybe date. And we'll be explicit. We'll set it to null for now. Now, if we look at maybe date, the value, again, is date time. So it's still a nullable, but it's got a type parameter that is going to be used throughout that class, the nullable class, in order to represent return values or parameters of properties and methods. So our value has the date time. Again, if we went to the get value or default, the return type is going to be a date time, but it may be a valid date time, or in our case, it's going to be the default. So let's go ahead and do get value or default. We can write that out. And we'll see if we run this, what do we get? We got a build error there. Oh, didn't like my X. We'll call that A because I already have X down below. There's our JSON person, and there's our default value of the date. We said get value or default. Default is January 1st, 0001 at 12 a.m. So when you're using generic types, you're going to provide one or more of these generic parameters, and that's going to influence parameter types, return types in that class or for that method, depending on the scope at which you're using the generic declaration. We've seen how to use generics. Let's look at how to define them. I'm going to right click on my library here and add a new item. I'm going to choose interface. I'm going to call it iMapper. This is something I've used recently in some client scenarios where I needed to map multiple types. We're going to make this public instead of internal. And I'm going to define this interface with generic types. So I'm going to say S and T. And what that means is I've got two different generic type parameters. And then I can define a method inside of this particular interface. So I could say I'm going to return a T. I'm going to call it map. And then the method is going to take an S, and that's going to be the source. So this interface says, give me two types. And I've used S and T here for source and target, the source type and the target type. And that's something you'll want to do when you define generics, is come up with good values for those type parameters. It may be simple letters like this, or for example, you might use T key to indicate that the type is for the key. So now they've got an interface. Let's go create a new class. So we've got our person. We'll go add a new class. We're going to call that customer. That'll be our customer class. And we're going to map from a customer to a person. So I'm just going to cut this and we'll just paste the customer in. So it's very similar to person. It has an ID and a first and last name, but it has a create date instead of having an age. So we'll save that. We'll go create another class. And this one's going to be our actual mapper. So I'm going to call this my customer to person mapper. We'll put that in there. Again, we're going to make that public because we're going to want to use it. And I'm going to implement the iMapper. And now for those types, the source is going to be customer and the target is going to be person. And if I go over this, it's going to tell me I'm not implementing that method. So we'll go ahead and implement the interface. And notice the method that gets generated. It's a public method called map that takes in a customer and returns a person. So we could simply come in here and return new person. We'll use the object initialization. We can say the ID equals source.id. That'll be the same. We can say the first name equals source.firstname. Last name equals source.lastname. And we have the age, which is an int. And so that's just going to end up being 0 because we don't have a value for it here. But we could go in and put a default value there or provide some other value. So a very simple example. You'll notice I defined a type, in this case an interface. Could be a class as well, just like that, with two different types. And then I've implemented that here because I'm having a concrete implementation of that interface. We'll go out to our program. Let's go ahead and we'll just get rid of all the bits that we've had so far. We'll go back and we'll use our Essentials 2 library. Get that back in. And now we can do a new customer. And again, we can have an ID. We'll say that's 7. First name equals customer. Last name equals first. Just to be a little confusing. And then the create date equals new date only. We can specify that a number of different ways. We're going to go ahead and do option that allows us to do year, month, and day. So let's do 2022. Let's say it's January 17th. And now that's our creation. Got my semicolon in the wrong spot there. We've got our customer. Now we can create our mapper. We've got our customer person mapper. We could do mapper.map. And now we can pass in the source, which is that customer. And what we'll get out then is a person. Of course, we could write that out. p.firstname, so we can see what happens there. Notice at this point, I really don't see any of the generics. I've got a class, customer to person mapper. It's got methods on it. It's very strongly typed as I would want so that I can use these very specific types. It's that interface that's very flexible for me now. I can create another class that's a different kind of mapper, still implements this interface, but the types can be different. So we'll run this quick, make sure that everything builds and we get the expected outcome when we map our customer to a person. And there we go. We've got the first name mapped onto the person, comes across as customer. Now, as we've seen, we've got those types that can have a generic. You also have methods. So we can add a method here, and you can see how we can combine these type parameters. I want to say I've got a public method that's going to return a type T called map of t. That's how you generally refer to these generics. So you're going to be able to provide the output type. In addition, you're going to need to provide me the mapper. I'm going to say provide me a mapper. And remember, it was source and target. And the source type is going to be customer because I'm mapping from within this customer class. It's going to be a set source. And then the target is going to be that type t. What we've got is a method called map of t that will return an instance of type t as long as you give me an IMapper that has a source of customer and a return type of t. So I'm going to call this mapper. Come down here and we can simply say return mapper.map, and we're going to pass in this, the customer. So that mapper, because it's an IMapper of customer t, is going to be able to return a t. We go back out to our program here. We can go right here where we used our mapper before. Instead of calling the mapper directly, I can use the customer.map method. I'm going to map to a person, and then I'm going to pass an IMapper of person to customer. So I can pass that in there. And again, we can run this and we should get the same output we got before, which is customer. So that's an example of a generic method where you specify that type. And I also want to point out that you can pass those type parameters to additional generics, as well as use very specific values like the customer that we did here. I want to look at another concept around generics, which is the notion of constraints. So I'll right click over here. We'll add a class. I'm going to call this sorter.cs. So the idea is that I want to create a class that's going to allow me to sort something. Maybe I'll do a sorter of t, and I want to be able to then sort a set of items that are of type t. So I create a method, say public void sort. We've already got the type up there in the class definition. So now I can just say it's an array of t called items. And now I can start implementing my sort. The problem is I don't really know what t is, and I don't know if I can compare them. For example, I could look at it and say if, I could say items, we'll assume that there's more than one for now, the bad practice in our index. We'll say, well, if that's greater than the other, but the problem is since we don't know what t stands for at this point, we can't really identify a comparison because we don't know if the type supports the comparison operators. So what we need to be able to do is indicate that that type t has to follow some rules in order for us to be able to use it in our class. So we follow that class definition with a where t and then colon. Now I can say things like, I want to make sure it's a class, or it's a struct if you want to do that. I can say that it derives from a particular type, or in my case, I want to know that it implements a particular interface, IComparable of t. Meaning if you want me to sort a person class, if that's the t you're going to pass in, then that class needs to implement IComparable of person. You can additionally indicate that something supports being created or constructed with an empty constructor. So if you need to create instances within one of your methods, you can stipulate that that's one of the rules that that type has to implement. With that in place, our sort implementation becomes a little easier because you can now implement a for. I can say for I equals 0, I is less than items.length. And actually, I'm going to set I equal to 1. I want to start with the second item. We'll assume we've got some items here. Should do some error checking or bounds checking. Then I can say if items I dot compare to, we're using that IComparable now, items I minus 1. And we could say if that's less than 0, that means we know that this particular item at the second index is less than the item before it. We want to swap those. So we might do something like this. We'll say swap past the array, and we'll pass I and I minus 1, and we'll swap the positions of those two things. So we could come in here, we'll add a little swap method similar to what we did before. So I've got swap, an array of t called items and the two indexes. I'm just going to swap those items out. By using this constraint, the compiler knows that whatever T stands for, whatever that type is that gets used, it's going to be able to support this compare to method because it has to have iComparable of T. So we can go back over to our customer now. We can say that it's going to implement iComparable of customer. So if we want to create now a sorter for customers, we can do that. Implement the interface here for the compare. And again, I'll just paste in a little bit of code so you don't have to watch me type that one. We'll say if the ID of the other item is equal, then we return 0. That's what the iComparable definition would indicate. 0 is equality. If the other ID is greater than this, that means we're smaller. And so we're going to return a -1. Otherwise, we'll return 1. So when we compare customers, we're essentially just comparing the IDs. Whatever your class definition is, whatever it means to compare two things to indicate if one is greater than the other, that's the logic that you'd put in here. So now we have an iComparable, and we have our sorter that's a generic class that requires an iComparable. We can come back out here. We could create another customer. We'll pass that in. We could say, oh, that's got a lower ID of 3. We'll call that customer 2, and we'll just change the last name to second. And then we want to be able to create an array of those items, and we want to pass it to the sorter. So let's create the sorter. So now it's a new sorter of customer. Get that on the screen a little better there. And we need an array of customers. So let's say customers equals new customer array. And we'll just put C and C2 in there. We've got our 2 instances. And now we can sort that. Sorter.sort. We can pass in customers, and it should sort that array of customers for us. So we can do a for each customer in customers. And then we can write something out here. Maybe we'll do the customer ID. And then we can just do a colon maybe, and we'll do the customer last name. Go ahead and run that while it's building up. And so now we have our sorter of T, which we've identified as a sorter of customer. We've got our array of customers. Customer C has an ID of 7 and C2 has an ID of 3. So they're not currently in low to high order. We execute our sorter, we loop through, and now we can see those items have been sorted. 3 and 7 are now the indexes as they are in order in the array. Not the most efficient sort algorithm. That's not really the focus here. I just want to show you how to use these generic definitions to make more flexible classes and to use the constraints on these generic types to make sure you can operate on the instances of those types to fulfill your class's purpose. And we'll look at generics a bit more throughout the class, especially as we talk about collections up next. Now that we understand generics, I want to look at a particular part of the base class library that you're going to use regularly in your C# programming. And we're going to see that it's a good use case or candidate for using generics later on. I'm going to clear out my program CS here just a little bit, and I'll paste in a little code. So you can see I've got an array of strings with a couple of names in it, and then I'm just doing a console write line, and I'm writing those names out. So it's going to write out hello, Matt Milner. And that's fine. And arrays are a great way to manage collections of items or manage more than one instance of a type. So we've been focusing on creating types, whether they're generic or our interfaces, our classes, structs, and records. But now we're going to work with multiple instances, and we need a way to do that. And again, arrays are fine. You've probably used them if you've done programming in other languages. Got this concept of zero-based indexing, where we can index through each of those in order to get particular items or set their values. However, collections are going to make working with multiple items a lot easier for us. So we're going to start where most people would start, and that is we'll create an AL variable here. We're going to say new system.collections. And this is where most people would get in and say, great, this is where I go when I want to create collections. Array list looks pretty interesting. Let's create a new array list. When we created our string array up top, we gave it a capacity. I can do the same thing with array list. And now I've got a class and I could go add items to it. So I could take that and I can now add. And if I wanted to, I could add in, say, the word first. So we can see that we've got a particular item in there. If you notice, looking at the signature of add, it takes an object. So we can pass any type in here. We can use an array list to manage any type. Let's take a closer look at array list. I'm going to use F12. We can use right click and go to definition. You'll see that the array list implements three very important interfaces when we're working with collections. We'll start with IEnumerable. So again, you can right click, go to definition, or you can press F12. You can see that the IEnumerable interface has one method on it, getEnumerator. And that enumerator, if we go there, is going to give us the current item. It's going to allow us to move next or reset, essentially to enumerate through the items in this collection. We go back to, we can see iCollection. And if we go look at that, notice that iCollection also extends or inherits IEnumerable. So if your class, your collection implements iCollection, you can also enumerate through it using that interface. And collection simply gives us a notion of a count, how many items are in there, the ability to copy it to an array, and some notion of synchronized access. We'll get into that a bit later. And most importantly, iList. This is the interface that you're going to use most often with your collections, and you'll see that it also extends that iCollection and IEnumerable interface. And we've got add, insert, remove logic here. We've got a contains check to see if something's in there. And we have indexing, just like an array, where we can go in and access items at a particular index. So this really gives us that list functionality. What you'll notice though is my string array up above had a size of 2. And you've probably run into this if you've done any programming where if you go above or below that index, you're going to get an error. With the array list, however, I can go in and say I want to add a range. I could say I want to do a new string array. I could come in here and do second, third, and even fourth. So now I'm going to add all these items to that array list. Now the initial capacity I set was 2, but the array list, unlike an array, can actually expand to handle more items. Obviously, we'd want to provide an initial capacity that is close to what we're going to use, so all the space gets allocated, but we're not constrained like we are with arrays, and we don't have to do that allocation ourselves. Now let's use some of those interfaces. So for the iCollection, we could come in and say collection size is, and we can use that AL count. So that's that iCollection. We could also get an indexed item. So we could say indexed item from collection, and we can do 2 here. So we're saying that's where we're going to get that value. And I'll use a different model for the string formatting here, where I just put the index of the parameter in those curly braces. And I'll say AL2. So we're going to get that item. So using that iList interface, we can index into that collection and get a specific item. And then we could do something like this. We'll say all items in the list. And now we can do a for each. So that for each, say var item in, and our collection is our array list. And now I can just iterate over and pass that out. And this is that IEnumerable. The for each is going to enumerate over those items in the collection and write them out. So we run this, we should get first our output from the string array. It says hello. Then we see the collection size is 4. So we started with that first string. We added a range of 3 and it expanded from its initial capacity of 2 to 4. We're able to get the indexed item. You can see that zero-based indexing means that's the string third. And then for all items in the list, we iterate through and we get first, second, third, fourth. And so that gives you a general sense of the notion of collections that you can use in C# from that base class library. But I want to caution, we'll talk about this next, that the system collections namespace isn't necessarily the best place to start. You've got some hints of this from our earlier conversations around generics, and of course, what we've seen here, where everything is an object. The array list is a great improvement over a basic array. It's a little easier to work with. We can do a number of different things because it implements those 3 key interfaces. But I've added this collection samples file into the library project. So if you're following along in the exercise files, you want to grab them for this particular movie because I've got this new class in here, or you can type it out. And it's just a static class with some static methods, an example we learned about in C# Essentials 1. And I've got 2 methods in here. I've got one called queue and one called stack, just to show you the different collection types are available for different types of collection management. You can see with a queue, we can enqueue multiple items, as I've done on line 8 and 9. And then I can dequeue items. I can pull them out of there, and I can then write out that value as I've done from line 14 through 18. Notice on line 17, I'm actually checking that the queue has something to dequeue. I'm using that iCollection interface to let me know, is there anything else that I should pull out of here? And if not, then I'm going to break, because if I call dequeue and there's nothing there, I'm going to get an error. The stack works a little differently. So a queue is first in, first out. So I've got first item, second item. When I dequeue, I should see first item, second item. The stack is last in, first out. So I'm going to push things onto the stack. So I'm going to push first item, and then on top of that, I'm going to push second item. And so if I go through these with that same kind of while logic, popping instead of dequeuing, then it's going to pop the top item. So I should see second item, first item. So if we go back to our program out here, we can use that collection samples. I can call queue. That's going to run that method. Call that again with stack. And I can even throw a return in here just so we don't see the other bits of code we've got from our previous examples. And so the queue, again, first in, first out. We should see first item, second item. Whereas the stack, we see second item, first item. Now, if we look here, what's something that stands out to you? If you were listening in the last movie, I talked about the system collections namespace. And you can see that when we pop items off the stack or when we dequeue from the queue, I'm having to cast that result to a string. And that's because, again, these are based on the notion of objects from the early days of .NET. We have these original .NET collection types in that system collections. So we have the stack and queue for that last in, first out, or first in, first out, that ordered insert and removal type operations. Got our array list for simple collections of objects, works like an array, but dynamically expands and gives us more capabilities. Got a hash table for using a hash of a key to look things up. Got a dictionary base, which allows us to have a variety of different implementations for a dictionary, again, a key value sort of storage, sorted list, and a name value collection where we can have a name that has one or more values. But as I mentioned, all of these older types, these were around from the original .NET from early 2000s, almost 20 years ago, are obsolete. You can still use them, but instead, you're going to want to use the generic collection types because they're going to give you better performance. They're going to be easier to work with in a typed fashion. So instead of just a stack, we'd use a stack of T. Instead of a list in the array list, we use a list of T. It's probably one of the most common collection types that I use. Instead of a hash table, you got a dictionary. And here we see multiple generic types provided. What type is the key and what type is the value? Same thing with dictionary base or sorted list. We have generic versions of sorted list, sorted dictionary. Now the name value collection, because that was all strings, is still valid. It's used throughout the framework for things like HTTP cookies, for example, where you have a given name and you can have one or more values associated with that name. As you can see, there are a number of different collection types, each with different semantics for how you use them. Again, the list is the one I use most often because I often just need to manage a collection of items, with dictionary probably being the second most used for me. But you may have programming concepts in your applications where the stack and queue are really relevant. If we come back in here, I'm just going to change this, and instead of system collections, I'm going to do generic, and now I've got a stack, and I'm going to change it to a stack of string. So it's a stack of T, I'm providing it a string. Now I can get rid of this cast, because if I look at pop, it's going to return a string. Now strings are pretty easy to move back and forth from objects, so it's not quite as exciting. Could easily have been one of our person or our customer classes we've been working with as well that we could push or pop on here. So it shows you just how easy it is to use those generic types, but it gives me a much cleaner interface, gives me better performance because I'm not having to convert or cast between these items. Of course, we run that and we should get the same output we had before. We could go through and change the queue to a generic queue of T, but I'll leave that to you to try on your own. I want to talk about some of the different ways you'll use these collection classes as you write your programs in C#. If you're following along with the exercise files, you want to grab the ones from the begin folder for this section, as I've added some things here to our collection samples class. Remember, it's a static class, so I've added a static field called customers of type list of T or list of customer. And I have a static constructor here on line 42. So I'm initializing that customer list into a new instance, and then I'm going to iterate through from 1 to 11, and I'm just going to add a new customer for each index of I. So the first name will just be whatever I is, and we'll write it as a string. Last name will always be customer, and then we'll create a date, slightly dynamic. It'll always be October of 2021, but we'll have the day be whatever that index is at the time. So now we've got a list of customers. What can we do with that? Well, in this indexing method, it's just a driver for some of these examples. You can see that I can use the indexing just like I would an array on line 60 to grab a particular customer out of that list. So even though it's a generic list instead of an array, I still get that same easy syntax to grab a very specific item based on position. So we'll find that and we'll write out to the console, hey, I found this customer with this particular ID at this index. That says index 2. Next, on line 64, I'm going to use something that's a little more advanced, which is the contains method. So I check, does customers contain a particular customer? And in this case, I'm using that variable customer 3. That's the item I just pulled out of the collection. So we would expect that that does in fact come back as a true. That means our string does contain will be does, and we'll write out customers does contain this customer. So before we move on, let's run those two. I'm just going to run this real quick. We're going to have a little extra content on our screen here that we'll get to. But we can see found customer 3 at index 2. So that indexing piece that we just saw. And then customers does contain this customer. Now as a follow-up, I've got a couple of extra challenges you can try here. What do you think happens if you create a new customer object with the same property values? So it's got the same ID, first name, last name, and the create date. If you ask, does the collection contain that item? What's it going to say? If you add the item and check it, what will happen? And then again, on line 67, same thing. You want to create a customer object, but what if customer isn't a class or a reference type as we've got here? What if it's a record type or a struct? What happens there? Just a couple of things for you to try out to understand how the collections might behave differently with different types. You can go back to C# Essentials Part 1 if you need a refresher on some of the differences between those reference types and value types or records. And finally here, we've got a predicate to find an item in the collection. So this is another great feature of the list. Beyond just holding those items and being able to either index or walk through them, we saw we could see if a collection contains something, but we can also find a particular item or find the first item that matches. So we use a customers.find, and this takes what's referred to as a predicate, which is essentially a method that returns a Boolean value. So you can see down on line 83, I've defined a method called customerIsMatch. It takes a customer and it returns a Boolean. Now in my instance, I'm simply doing a check to say, is this the customer with ID 7? Does this customer object that you're passing me have an ID of 7? If so, I'll return true. Otherwise, this would return false. So when we call customers.find, it's going to look at the customers and it will take the customers then, call this method. As soon as it gets a true, it's going to give us back that object. And so we should be able to look and see that we do get customer 7. Again, we run that. We can see that was our third line there where it says found customer 7. Another follow-up option for you here, you can change what this customerIsMatch does. Maybe see what happens if you match on last name. All of these items have a last name of customer. Which one's going to get returned, if any of them? So those are a couple of different ways you can work with that list of T and a number of other collections. When you want to find objects, you can also insert, you can remove, you can find the index of items. So instead of finding the actual item, you could find out that a particular item is at index 3 if you wanted to. And then the last bit here is this notion of iterating over the collection or working with the collection as a whole. And so there's a couple of handy methods on the list. You'll see on line 92, you have the option to reverse the list. Now this doesn't have anything to do with sorting or looking at the objects in a particular way. It simply takes them in the order they are and it reverses that. So we've got our 1 through 10. When we reverse, we should now be 10 through 1. And then I want to show you 2 different ways to work with that IEnumerable. You can see on line 94, I can explicitly get the enumerator for that collection. And on line 95, I can call move next on the enumerator. And if that returns true, that means it was able to move to the next item. So I go in there on line 97, I can get the current item from the enumerator, which is going to be my customer, and I can write that out. So this gives you very explicit control over that and a very manual process to move through. On line 105, you can see the much simpler option. If you just want to iterate through them and do something, you can use the for each. So we do for each, customer and customers, and then we can write out that value. You can work on that customer object. This is a lot simpler, but essentially is doing the same thing as what you see above. And just for fun, on line 102, in between those two things, I called customers.sort. Now, in our case, customer, if you remember, implements iComparable of customer. I've simplified the implementation of the compare to method here since we were just comparing IDs, but this is what's going to get used then if we call sort. So it's going to sort that based on the iComparable that we've got set up. So if we go back out to our program, you can see we were running the indexing here. I'll go ahead and comment that out and just run the iterating. And let me go back to our samples. So we reverse the order, and then we use that enumerator to walk through. You can see we do have them in reverse order, 10, 9, 8, all the way down to 1. And then we sort using the iComparable that sorts on ID. So when we use the for each, they come out 1 through 10. Hopefully that gives you a sense of how flexible these collections are and some of the great features that have been added on top of the concept of just a basic array. So this notion of being able to work at various points, be able to find items, add items at different points, iterate over the items in those collections, makes them a critical piece of most C# applications that you'll write. We're back in our collection samples file here, but I have updated it with some code. So you may want to go to the begin directory for this particular movie and load that up if you want to follow along. I've added this dictionary method. I want to show you how to work with those generic dictionaries. You can see here on line 115, I've created a generic dictionary where the key type is string and the value type is person, meaning The key, what we're going to use to uniquely identify this item and look it up or index it, is a string. And what we're going to get back or put into this dictionary is a person. So the dictionary gives us this really great way to store a set of items, but to have that unique key to go and work with that specific item. So we don't need to know its position in there. We don't need to go find it. We can directly access it by that key. And then on the next few lines, I'm just adding 2 new person objects. So I've added a person for me, person for Larry Lawnmower, and I've given each of them a key with just the letter that I'm using in my alliterative names here. Now, quick question. Is this a good key? No, it's not. It's a terrible key because it's not very unique. M is one of 26 letters in the US alphabet, and that's not going to give me the uniqueness I need. So we're just using this for examples here, but you're going to want that key to be unique to that item. And that might mean it's not a string. Maybe it's a unique identifier. Maybe it's an integer or another numeric type. You can define your dictionary then with that key type. Now, a couple things we can do now that we have this dictionary with a couple of items in it. One, we can use the contains key method on that dictionary to find out if that item already exists, specifically an item with that key. We aren't really looking at the item itself or the value. We're just doing the key because that's going to be the quicker lookup. That's what everything's going to be indexed on. So we can find out if that collection contains the key, and then we could safely go and access that particular item. So you can see on line 138, I'm going to use the result of that contains key, my key found variable. And if that's true, now I know it's safe to go in, use that key to index into the dictionary and get out a person, and I'll write out the first and last name. If I don't check that, if I try and index in and the key doesn't exist, I'm going to get an exception indicating exactly that. Here's a follow-up that you can do if you want to try this out on your own. Line 143, there's a try get value method on the dictionary. It's going to allow you to provide a key. It's going to give you back a Boolean value indicating whether it was able to get the item, and it's going to use an out parameter. So that's another good way for you to be able to safely try to get a value based on the key and already have a true false value letting you know whether it succeeded. And finally, for the dictionary on line 145, you can see I'm going to do a for each over my dictionary. Now in this case, that's going to use the IEnumerable and the enumerator to allow me to walk over that. And because that's a var, we don't necessarily know the type. I like to use var when I'm working with collections and enumerating, so I can mouse over like this, and I can see that the type of that item is a key value pair of type string and person. That means I'm going to get a class or an object that has a property called key, that's a string, and a property called value, that's a person, and I'm going to be able to work with that in my iteration. So now I can write out the item key, which is going to be that string, and then the item value, since it's a person, I know it's going to have a first name and a last name property on it that I can access. So let's go run this dictionary code. We've got our 2 people added in there. We're going to check for that M key, and then if we find it, we'll write out that person, and then we're going to iterate through both items in the dictionary. So back in my program CS, you can see I'm just calling collection samples dictionary. So our first line, person with key M, is Matt. So it found that person. It was able to validate that that key did exist and then index in and get that. And then we iterated over and we got the key and value for each of those items. Now, if I try to, say, take this L and I want to add a new person, we'll call it Letitia. And we'll just change the ID to 3. Because I've already used that key, I'm going to run into some problems here. I'm going to start this again. We'll run it. You can see an item with the same key has already been added. So dictionaries require that that key be unique. So here's another item for you. We'll put it in here. So I'll follow up, use the try add method to try to add this person and see what kind of success you have using that as a safe way to try and add something and get back a Boolean value indicating whether you were able to add it or not. And lastly, I just want to quickly go over the name value collection because we have seen how we can use the dictionary with a unique key, but I've also mentioned that the name value collection allows you to use the same key for multiple items. So if I go out to my program CS here, we'll uncomment and we'll comment. So we're going to be running the name values real quickly. We'll see we've got Matt and Letitia. Those are the two that I've added there, but let's say we want to bring Larry back in. So we want to items add, we want to use that same name, L, but now the value is going to be Larry. What's going to happen here? This isn't a dictionary. That's the name value collection. So for each of these items then in all keys, notice on 166, I'm iterating through the keys. And then on 168, I'm actually indexing into the name value collection based on the key. So it's slightly different. We don't have the key value here. We have all the keys and we can access those values, but I'm simply going to iterate the keys and then index. And notice that for that key, L, we get both Letitia and Larry as values for that. So the name value collection is really handy as it provides a different semantic for working with this where one key or one name is able to have more than one value. To finish up our conversation on collections, I want to mention one other namespace, and that is the concurrent namespace. So I'm going to do another method here. We'll call it public static void concurrent. We're going to add that in. So let's say we've got a bag equals new system.collections.concurrent. And if you look here, we have a smaller set of collections in this concurrent namespace. So the key ones are concurrent bag, concurrent dictionary, concurrent queue, and concurrent stack. Those are the primary ones that you're going to be able to use out of the box, similar to what you've seen with these other collections. So let's go with a concurrent bag of person. So it's a generic type. If we go to bag, we can see there's a lot of different options here, but it's going to work very much like the list or some of the other ones we had, where we can add items, we can pull items out, we can find those items. But what's different is these collections are set up to work in a multi-threaded environment. We're going to talk about threading and multiple threads a bit later on in this course, but because we're talking about collections, I wanted to make sure we touched on these. So I could add a new person. So we could do first name, just like we've done before. We'll get the last name, age, and an ID. So we've got a person, we could add another person in there. And where you want to use these concurrent collections can differ, but primarily the first thing you're going to think about is, am I going to be accessing this collection to add or remove or update items? If you're simply going to be reading items, then the concurrent dictionaries may not really be necessary because you're not going to be changing that collection. It's okay to read items out of there and work with them. But just like before, we can do a for each. So we can add our bag here. And then we can write out for that item. We've got it's a person. So we could do something like first name. So again, I don't want to go into a lot of detail on these, but I want you to be aware that they're here. We'll revisit when we talk about threads and understand that if you are going to be in a multi-threaded scenario where you're adding or removing items from your collection, you're going to have to think about concurrency. You're going to have to think about using one of these thread-safe collections. There's good guidance from Microsoft in the documentation about the comparisons between, say, a concurrent stack of T and a stack of T from the generics namespace, and when you might use each. But that general rule about the updates and adding is the first place to start. So we could come back out here. We could add our line for our collection samples concurrent, just to make sure nothing is broken. We'll run that and we should get that output that we expect from the person first name. So we've got Larry and Matt. So Larry and Matt, if you'll notice, when we added these in, we added in Matt and then Larry, but when we read them out, when we iterated over them, we got Larry and Matt. And so this particular bag is unordered. It's another key thing to understand is that a bag is different from a list. So that behavior may change if you're switching from, say, a list of person to a concurrent bag of person. Keep that in mind as well as you choose those collection types. I want to start talking about exception handling, dealing with those cases where something goes wrong. If you're following along with the exercise files, in Chapter 3, 01, begin, you're going to find that LinkedIn Essentials 2 solution, and I've added a few things to it. So if we go over here and look, you'll see over in the library, I've got an employee class. That's a simple record type of employee with an ID, first name and last name. I've got a JSON file in the LinkedIn.Essentials 2, the main program, that just has some JavaScript object notation or JSON of an employee. It's got that ID, first name and last name. And in the program CS, I'm going to call out to exception samples.basicExceptions, which is a new class, exception samples that I've added, and a method that wraps up this example. What we're going to do is take that JSON file, try and read it in, and deserialize it into an employee. And you've seen bits and pieces of this before. So I've got two different paths, a wrong path and a right path. The right path is how we're going to get to that mat.json file under our project, and the wrong path is just the file name, which would throw an exception. So here on line 13, that's where I'm going to choose to either use the right path or the wrong path. I'm going to use a file stream that I declare on line 14, and I'm going to write out the current directory. That's just so you can understand why the path I use for the right path is the correct path. And then we're going to go into the basics of the try catch. You may have seen this in other languages, so I just want to make sure you understand the fundamentals, and then we'll get into more specific examples and some of the intricacies in later videos. We wrap the code that might throw an exception in a try block. So I start my try block on line 16 and 17. Everything between that closing bracket on line 23 is what I'm trying. So if an exception happens there, I want to catch it. You can see that I'm opening a file. That can cause problems. I'm deserializing an employee from the file contents or that stream. That could cause an exception. And then I'm writing out that employee to the console, which hopefully won't cause an exception, but certainly could. And here that record type's built-in ability to have a toString that writes out its properties comes in handy as we write that out to the console. Line 24, you see we have a catch. So after a try, we have a catch. We define the type of exception that we want to catch. In this case, we're going to use the base system.exception. And then I use EX as the variable name for that exception so that I can use it inside the catch block. Here I'm writing it out to the console, just writing the message. Often you'd use a logging framework to log this out to a permanent store or some sort of system where you would alert somebody that there was a problem. And then we have the finally block. And this is code that's going to run regardless of whether there's an exception. So if we have no exceptions, we'll do everything in the try block and then the finally. If we have an exception, we'll do everything we can in the try block until the exception happens. Then we'll execute the catch block, and then we'll execute the finally. And so I need to make sure that file that I opened up gets cleaned up. I want to make sure that I close that, and I do that by calling dispose on that file stream. So let's go ahead and run this. We're currently using the right path. So you can see on the second line, it says employee read from file. We get the information from that JSON file. And that current directory, you'll notice at the end, in addition to the path of the project, is a bin debug .NET 6.0. That's where our code is currently running. And that's why if we just use the file name, it doesn't work. So if we switch this to the wrong path here, now we should see an exception happen. We should write out the exception, but we're also going to close up that file. So current directory prints, our standard exception is caught, so they could not find the file. You can see why, because it is looking in that bin debug net 6.0 format.json. One other important concept I want to point out here. I'm using this file stream and I'm managing it, but it's very important that I clean it up. And so I've followed this pattern of making sure in the finally that I call dispose. File streams, like lots of classes in .NET, especially those that access external resources, network connections, SQL database connections, for example, implement something called the iDisposable interface. And that means they have this dispose method to clean up whatever resources they might have. Often that might be something outside of .NET, like a file handle. So one of the things I can do is I can comment this out. I'm going to say using var file stream, and then I'm going to close that up. And now I'm going to use curly brackets. I'm going to come down to the end of my try block, and I'm going to close that out. What that means is I can actually comment out this cleanup because the using statement understands iDisposable, and what it says is for this block, so from lines 19 to 24, I'm going to have this file stream, but regardless of how I exit, if there's an exception or if I just fall through the control flow, I want to make sure to dispose of whatever the object is that I've declared in this using statement. So that file stream has to be something that implements iDisposable. So again, we can run this. We'll get our standard exception. We get the same kind of cleanup as we would have with the manual process I used before. And we'll set this back to the right path so we end with code that works. We're able to read that employee from the JSON file and write it out. We have some basics down. We're catching an exception if it occurs and we're logging it. But as I said, there's a couple different problems we might run into. One is file-based issue, trying to open that file and read it. And the other is with the JSON deserialization. So just catching an exception, while it will handle all of those, doesn't really tell us what the specific problem was. So one thing you might try and do is come down and catch an IO exception like this. And what we're going to see is that we're going to get a red squiggly telling us there's a problem. And what it's telling us is these catch blocks are in order. They're going to be applied in order. And that first one is going to match everything. So this guy will never get hit. Let's take it, put it up here. And now the more specific exception comes first. So if it's an IO exception, we'll do this logic. If it's not, but it is a regular exception, then we'll do that. So we can do something like this. We can say we've got a IO exception, and then we'll put that message in there. So we'll do IOEX.message. And now we've got an IO exception. Likewise, we could put another one in here and add another catch block for a JSON exception. So we've got that. We can add our curly braces. And now we can write out JSON exception. And then we've got our JSOEX.message to write that out. So if we change this back to the wrong path, you'll remember that should give us a problem with the file, and that should be an IO exception. So let's give it a try and see what happens. There's our current directory, and sure enough, there's our IO exception. Could not find the file, and then it gives us the path. Now, if we have a problem with the JSON, for example, let's say instead of a string here, I try and put a number, and then we go back to our samples and we use the right path. So we're going to have the path to the file correct, but the file has a problem. Now we get our JSON exception. JSON value could not be converted to a string, and it gives us the information about that particular exception. You can provide as many catch statements as you want. Again, you want to go from more specific to less specific. So for example, I could even add a file not found exception. And that is going to be the more specific IO exception. It actually derives from IO exception. So we'll just say file not found in that case. Now to get the file not found, I have to go back and use the wrong path again. Keep switching that back and forth. And now we just see file not found. So we're not getting the generic IO exception. We're getting the specific file not found exception. Again, if we go to the definition for that, you can see it does derive from that IO exception, but it's more specific and therefore matches first. So depending on what you're trying to do, how specific you want to get with your logging or your error handling, you can identify these catch statements for the different kinds or different types of exceptions and handle them differently. One last note here, you'll see that for the file not found exception, I get a little green squiggly, and that's because I'm not actually using that variable name, that fn_fex. So I can just get rid of that. I can tell it, just catch this exception type. I don't need a variable to hold the exception. I still want to run that particular exception handler for the type. So if you're not going to use that variable, if you're not going to do something with the actual exception, you can simply catch on the type and leave that out. It's great when you've got a specific exception you can catch that's very focused, like a file not found exception. That's a derived type of an IO exception that tells you exactly what went wrong. But sometimes the exceptions are more general, like a JSON exception. There's a number of reasons that there might be a problem with our JSON. So let me go back up here, make sure we're using the right path, because we're going to have a problem with our JSON, not our file location. And you remember I left this with this 809 for my first name. So let's go back here. We've got a breakpoint set in our catch block here. So let's run this in the debugger. You can see we hit a breakpoint, our JSON exception. If I mouse over or look down in the locals window, I can see a message that says the JSON value could not be converted. So that tells us we've got a problem there with a cast or conversion. So I'm going to add a filter here. I'm going to say when, then I'm going to put some parentheses, JSOEX message contains, I'll say converted. Then I'm going to use a string comparison. I'm going to use the ordinal ignore case. So basically saying ignore the case in there. I don't care if the capitalization matches. I'm really just looking for converted, and I'm not going to worry about specific language here. And so now my catch is very specific. I want a JSON exception where that message has the word converted in it. So I'm really looking for that particular problem that we just saw. So we should still hit that exception. Let's just run it and see. Yep, we get JSON exception. JSON value could not be converted. That's the exception message, exactly what we wanted. Now, if I go break my JSON a different way, let's say I have a string in there that's right, but as is usually the problem, I leave out a comma. Something simple that always seems to give us big headaches. So what would we expect to see here? Well, I can tell you that the error message we're going to get does not say anything about converting a type. So let's just run it. And notice we get a standard exception caught. That means we went into this exception block on line 38. It didn't catch a JSON exception. And you can see the error message there as it says the quotation mark's invalid after a value. It's looking for some other syntax. So because we filtered with that when clause, that particular kind of JSON exception didn't get handled by this catch block, but it did still get caught by the exception block. So here's a to-do for you. Add a catch block with a when statement to catch problems with syntax. Missing comma, for example. So that'll give you something to try out for yourself. So you're going to catch a JSON exception, but you're going to need a when block to make sure that you either specifically call out something about that kind of exception, or you make it somehow different from the when block that we have here. We've looked at catching exceptions, but now I want to take a look at throwing exceptions. When you get into a situation in your code where there's a problem, you may need to report that up through the application code as an exception. So I'm going to add a method here to our exception samples class called throw exceptions. Notice it's going to take a nullable bool. called should throw. And in this case, on line 59, I'm going to check if should throw has a value. If it doesn't, I want to throw an exception. Now, I could just throw an argument exception, but that isn't quite as descriptive, and I would have to provide a message and tell you what the problem was. If I throw an argument null exception, I get that more specific example. I'd simply need to provide the name of the parameter or argument to provide enough context for that exception to make sense. Now, if should throw does have a value and that value is true, I'm going to throw an exception, just as an example of how you do that. Now, you'll notice I've called out here that while I'm throwing a new system.exception, you really shouldn't do that. It's not very descriptive. It's very, very general. And we'll see next how to create your own exceptions to be more descriptive. But this will get the job done for now in order to throw an exception from this method. And then finally, if our should throw.value is false, then we're just going to write out no exceptions being thrown here. We'll save that, go back out to our program, and now I want to add some code here to call that method. So we'll paste that in. So we're going to use our try catch. I'm going to try the throw exceptions, and then we'll catch an exception and write it out. Now let's start with null here. So we can just pass null. Remember, if it's nullable, we should then see an argument null exception. And since we're catching it, we're going to simply write out all the information about that exception. Before we do that, we're going to comment out our old basic exceptions here. And now we'll run that. You can see at the top, we get a system argument null exception. That's our console write line there telling us that. Value cannot be null. That's the predefined message in that argument null exception, and then it includes the parameter that we passed in, should throw. Notice on line 3 at the end there, it's telling us this exception happened in exception samples.cs on line 61. And then 2 lines down, we see program CS line 17. That's where we caught that exception. Just keep that in mind. It's going to be important later on. Let's try again. If we pass in true, now we're passing this in and we should be throwing our system exception. So we've caught that. We're writing it out. I was told to throw this. Again, we see on line 3, exception samples, line 67. And again, then on line 5, we see the program.cs line 17, where we've now caught that particular exception. This is known as the stack trace. It tells us the various pieces of our application where this exception has been handled. So as you get deeper into a program, these stack traces can get pretty detailed and very deep, but you can see where did the exception start and where did it propagate up through the application code to finally get handled, in our case, on line 17 of our program CS. We've thrown and now caught exceptions. Now, one of the things you can do when you catch an exception is instead of writing it out, I could throw that exception. And there's 2 ways you can do this. I'm going to start with just the throw keyword, and I'm not going to pass it anything. And what that's telling the system to do is rethrow this exception EX as it was with its state. So the high level application is going to handle this or catch it. So now you can see on our first line, we have unhandled exception. That's something we didn't catch, we didn't write, but the application domain in which our code is running caught this unhandled exception. It's logging it out. We can see that's our system exception. And again, we see line 67 and we see program CS line 17, just like we did before. So we didn't handle it, we didn't write it out, but all that stack trace information was captured. Now, what you'll sometimes see is this. Somebody will say, well, I caught this exception. I'm going to throw this exception again. And let's see the subtle difference when we do that. There's a lot less detail. Still an unhandled exception. We still see the message, system exception, I was told to throw this, but notice what we get for a stack trace. We simply see program CS line 21. What's line 21? That's where we threw that exception. So by including it, we've lost the stack trace. We've kind of started over and said, here's the level at which you're going to get the detail, or here's the point at which the detail will start. So I generally don't use that. You may have some use cases where you do provide that. I'm going to go ahead and just comment it out so you can see it there. But generally, if you want to rethrow an exception, you would use the throw without that. Now, you can do both. You don't have to just throw or log or handle the exception. We could still log this exception to our logging framework or something else, and then throw it because we want code upstream to be able to deal with it if it impacts that part of the program. If we go back to our exception samples here, remember I said not to throw this general exception. We want to be more explicit. We want to provide more information when we throw errors. So I'm going to come out here and I'm going to right click on our library project. I'm going to choose to add a class. In this case, I'll just call it an invalid option exception. Mark that public, and we'll derive from exception, so our system exception. And then let's give it a constructor. So I'm going to type CTOR and tab twice. And we'll say that it takes a string called message. And we're simply going to go to the base and pass that message. So our constructor itself is pretty simple. Save that. I'm going to come back to my exception samples. And let's take this. And now we'll change this to our invalid option exception. I was told to throw this. And let's see what happens. We run this. So this is if we get true passed in. If we come back out to the program, we are passing true. We're going to write that. So we can see essentials library invalid option exception. I was told to throw this. We've got our write line, which is that first big block, the first 6 lines up there. And then the unhandled exception, because we threw it, it's getting written out again. So that seemed to work. We have the invalid option exception, worked just like the exception, but it's a little bit more explicit. However, you are going to likely run into problems with this definition in certain scenarios when you try to use this exception class. So we're going to want to do a couple things. We're going to want to mark this as serializable, meaning this particular class can be serialized by the .NET framework if it needs to take the class instance and write it over a network, write it out to a file. So that's one piece. We're also going to want to have some additional constructors. So we'll want a blank constructor, and we're going to want to pass down to the base in there. And then we want another one that takes both a message and an inner exception. So we'll do our trick there for CTOR. We're going to take our existing bit up here just to make it simpler. But then we're going to add to that and say exception, inner exception. And we'll pass that in as well. So now we can take a message as well as an inner exception. So for example, I catch an exception and now I want to throw a new exception, but I want to hold on to the context of that one so I can wrap it together. So I'll show you how we do that when we're done here. And the last one to follow these best practices for the serializable, and this one we can actually make protected. So we've got our invalid option exception. And here we want to take a serialization info. Now that's not coming up right now because we need to add system runtime serialization up at the top. So using statements. I'm going to add that in here. Just hit Control period to get those options. So we'll call that info. Then we're going to take a streaming context. We'll just call that context. And then we'll go to our base. We'll do info and context. Looks like I've got one too many parentheses on there. So we can clean this up a little bit. Of course, you can add logic into these constructors if you want to, but this gives us the base construct for this exception. So again, this is for certain scenarios, something you'll need in terms of this bottom one, especially for serializable and the serializable attribute. And then the others are really to give you more options for creating this exception. And by you, generally mean yourself, but also other developers that are going to use your code. If they need to throw this exception, they can throw it with a message, they can throw it with a message in the inner exception. So we'll save that. We'll come back out to program. Remember when we caught the exception, we were throwing it. One of the other things you can do instead of throw EX is you can throw a new, we could say application exception. And so we can add something like this, app exception, but notice that inner exception. And here we can pass in, that would be our invalid option exception. So we're creating an exception, but we're providing the context of the exception that we caught. So let's see how that all looks when we run it. There you see at the top, our write line. So again, we still have our essentials2 invalid option exception. That really doesn't change. It's when we get to the unhandled exception on line 7, where it says system application exception, app exception, that's what we put there. Then inside of that, we can see the inner exception, that invalid option exception. I was told to throw this and all of the details that go along with that. So we've seen two key things there. One is if you're writing your own exception class, yes, you derive from exception, probably an empty constructor. These other two with a string message or message and inner exception. And then add that constructor with the serialization info and the streaming context, as well as the serializable attribute in order to make this something that can be serialized. And we looked at how you can throw an exception and wrap another exception that you've caught inside of that as the inner exception, so you get more context. And again, you don't lose that stack trace, but your exception in this case should provide additional context or should be providing additional ability for the calling code to catch a very specific exception. And in this case, you don't lose all the context of the original problem. Next, I want to take a look at threading. Now, we're not going to get too deep into threading. It's a fairly advanced concept, but I do want to talk about some basic language constructs that make working with multi-threaded applications or APIs a lot simpler. If we start by looking at some basics around threading, and you may be familiar with this if you've used multi-threaded programming in other languages. The idea is that when we run an application, we have this main application thread, and that's going to sequentially execute the commands in our program. But sometimes we need to do something like access a file, and that can be a long operation. If it's a large file and we need to read it or write to it, then we may want to do that on another thread. And what that allows us to do is move that into a separate area of execution where that doesn't block the application itself. Now, this is really useful if you're writing, say, a desktop application, and that main thread happens to be controlling the user interface. You don't want to have some operation that makes it freeze up while you wait for that file to be read. Similarly, network access may be something else that you would put on a different thread. Anything dealing with I/O, where you're reading or writing to some sort of stream, or if you've got really intensive computations that might chew up a lot of processor time. So you can see we spin off or create these additional threads, and then when that work is done, we need to join back into the main application thread. And all of this can get fairly complicated depending on the programming interface you're using or the programming language. One of the things that I love about C# is how much easier it's made working with these kinds of APIs. And you're going to see that they're very standard in C#10. If we go back to our example code here, I have added some things. So you'll want to grab the exercise files from the begin folder. And you'll see I've added this item over here called thread samples. So we've got some items in there. I'm going to go back out here before I forget. We'll comment out our exception code from before. And then I'll do thread samples, simple thread, so that when we run this, we'll execute my code here. And I should point out, I've also fixed the mat.json file. We're going to use this in these examples. And so if you've pulled that across and you manipulated it to cause errors by taking that comma out or changing the value, you'll want to fix that. If we look at the thread samples then, what I've got is a method called simple thread. That's the one we're calling from our main program. And I'm simply going to change the color of the console text, write out the thread ID by using thread, current thread, manage thread ID, just so we can see visually that we're running on different threads. And then I'll reset the color. On line 18, I create a new thread, and I'm passing it a method called doFileWork, essentially telling it, here's the chunk of work I want you to go do on this new thread. On line 20, I tell it to start. Go create that thread now physically on the system and do the work in that method I gave you. While that's happening, I'm going to do a console write line here saying there's work happening in the main thread. And then I'm going to call thread.join on line 22. So I'm saying I'm waiting then for that work that's happening on the thread to complete. And that's going to be where I block. So we'll wait now. We've done other work in our main thread. Now we're ready to pull back in the work from the additional thread that's doing our file work. So what's the file work doing? Well, this should look mostly familiar. We're going out to that JSON file. We're going to read the text, and then we're going to deserialize it into an employee, and we'll write that out. Notice on line 33, I'm using a method on the file class called readAllText. Now our file is very small. That's going to be pretty quick. But if we were reading a large file, this is a potentially blocking operation in that IO category. We're going to read from that file stream, and it may take a while, and it may block this thread. So that's why we want to spin this off onto this other thread. So we'll call the simple thread method. It's going to create a new thread, run that code to read from the file and create our object. And we'll see what the results look like. We have our main thread ID. Its ID is 1. Notice then that we have work happening in the main thread. So that's now printed after we started the thread. Then we see the file access thread ID. That's a 7. And we get the output that's happening inside of that thread where the employee's been read from the file. We can make this even more clear. We could come add another one here. Say something like after all done. And we can see that that goes back then to that initial method, that simple thread method, after the thread has completed, and we can continue executing our main application logic. And that's the basic idea behind threads. Here, fairly simple to create a new one, start it. Then when I know I want to be done, I can join and do other work after the fact. But it's that join that can get a little complicated and managing what happens after the thread is done. So we'll see some additional ways that the language makes this even easier. With those threads, you can get some great benefits of being able to manage those and start up all that asynchronous work, but it is a bit of a struggle sometimes to manage all the threads as you get more and more of them. So there's also always been an asynchronous programming model in .NET. And I'm going to write a little pseudocode here just so you can see the old model, which will help you understand why the new model, the task-based programming with await and async, is a little bit better. Now in the old model, if we look at, for example, line 34 up there where we said we were going to do a file read all text, that's something that can take a while, and we might want to do that asynchronously. And so the old model, you would do something like file begin read all text, and then you'd need to provide the path, just like we did, so the parameters, but you'd also give a callback. So I might do finish read all text or something like that. You'd be able to name it, and you could have an object or something like that that was state that you were going to then pass into the callback. And then you'd have your method, the finish read all text down here. That's your callback. And that would then take in probably that state. Often had what was called an async result that would let you know the result of the operation. And you would then implement that method, and that's where you would do the work, right? So here's where you would handle the file contents, for example. This was great in the sense that it gave you that asynchronous model. So I could start this work, please go read all that text, and then I could move on with my program. And then when all of that work was done, I'd get a callback. So I would have this asynchronous model. Where the problems came in is that with this model, you often ended up chaining lots of these calls together. So you might open the file, and then you might read the file. And in fact, you might be reading from a stream. So you might be reading bytes over and over and over, and you'd have all these callbacks and all this state that you were passing forward. Now, all that, again, is the setup for what we have now. I'm going to paste in some new methods to replace the ones we had. So you'll see I have, instead of simple thread, new method on line 41 called simple thread async. And if you look at the method signature, you'll see not only is the name different, but I have a new keyword, async, and the return type instead of void is task. This is the task-based programming model. And using that task is going to allow me to do a number of different things. I've also added on line 52 a method called doFileWorkAsync that similarly has the async keyword and returns a task. If we start back at our simple thread async here, you'll notice on line 47, I'm going to call that doFileWorkAsync. But now I'm using another keyword, which is await. And what that says is, I want you to go start up this work, whatever's happening in doFileWorkAsync, you're going to give me back a task, that's the return type, and I'm going to await that task to complete. So this is essentially similar to that callback, but here is the callback code. So rather than having to write a whole different method, rather than having to separate that out, chain those things together, we can have our callbacks here. And in fact, then I could await some other work, meaning I can chain those callbacks together in what looks like a very linear fashion, what is very easy to read code. Looking at doFileWorkAsync, again, it has the async keyword and it returns a task. Notice on line 60, now I'm reading that JSON by doing file read all text async, and I'm awaiting that operation. So a couple key things here. One is read all text async. Just like I said, doFileWorkAsync. It's a very common pattern to put the async on the end of your method name to indicate that it's asynchronous or returns that task. And I'm also getting back a return value. So I'm awaiting that, but I'm going to put the result into my employee JSON. Notice it's a nullable string. That's because if we look at read all text async, it is an async method that returns a task of string or a task of T, a generic that we learned about. That means it's a task, so I can await it, but it's also going to return me a string. So after I've awaited, I'm going to get that string. And again, this greatly simplifies that model, where now I'm not passing around some generic state object or looking at an async result. I'm just getting the string from the operation that I wanted to call. In order to use the await keyword, you have to be inside an asynchronous operation. So that means your operation signature has to have that async keyword. Also, in order to await an operation, it has to return a task. So those are two key things to keep in mind as you look at this. So if we go back out to our program, we can come in here and do our thread samples. We can do simple thread async. And notice I get a little green underline telling me it's not an error, but I've got some information for you. And if we look, it's going to tell me that that is an asynchronous operation and you're not awaiting it. That's kind of like saying thread start and then wandering off. We're kicking off some asynchronous work, but we're not waiting for it to finish. And in the case of our program here, the next thing we're going to do is exit because that's our last line of code. So we absolutely want to put our await there so that we wait for that operation to complete before we continue on. I'm going to go ahead and run that. There are certainly scenarios where you might want to run an asynchronous operation and not await it. It's not as common, but if you want to start that work and you're not worried about waiting for it. You can see both outputs here now from our simple thread and our simple thread async. Both start on the main thread ID. Notice that in the first instance, the file access thread had an ID of 8, whereas in the second, the file access thread is still 1. And I'll go back to the code in a second and show you why, but we're still getting the same output. We're still getting that same work happening in that main thread. Looking back at the code, you can see there's that work happening in main thread. That was after all the work happened in our do file work async. So we awaited it. Once it was done, that was our callback essentially. That's where we went in and did some more work after that work finished. If you look down on line 56, that's where in our do file work async, we're writing out the thread ID. Notice that this is different from our first example. In our first example, we created a new thread and started it. That's why we got a new thread ID in that operation. We haven't done that here. We've just invoked an asynchronous operation. And while it was starting these first 4 lines of code, everything was synchronous. We set the foreground color, we did a write line, we reset the color, we set a string variable. Then only on line 60 do we actually start some asynchronous work. So at no point did we start up a new thread as we began this work. That's why we have the same thread ID, but there may be a thread that gets fired up in our read all text async behind the scenes for us. And we're awaiting that asynchronous work. We go back and compare this with our thread start. When we use the await, it's similar to doing something like this. We take the thread join, cut, and paste. We're saying go start that work and then wait for it to finish. And that's essentially what's happening when we do the await. So it's a little bit different. We're not starting up a thread and then being able to do a lot of work while that thread is happening. We're actually awaiting it, but it does give us that very succinct model for handling the callbacks when the work is done. And next, we'll see an option if you want to start up multiple pieces of work and wait for them all to be done. As we've looked at these two models, where we specifically create a thread and start and join, and then also when we come down here and used the async and await keywords, you may have asked yourself, how can I get something in between? I like this async await. It's very simple, gives me a very simple model without all those callbacks, and I don't have to manage the thread, but I would like to queue up multiple pieces of work. Let's look at how we can use tasks to do that kind of work. We'll take our do file work async here. I'm just going to create a parameter. We'll call it employee name. And then instead of my name, we're just going to use that employee name here. I'll put the $sign here to get us the string interpolation. So now we can actually parameterize this and we can say I want to do this work on a particular file. We'll copy and then paste our file here. Rename that. We'll call it Felicia. Open it up, and then we'll just change the name. So we'll call this Felicia employee, and we'll change the employee number here as well. So we'll say she was employee 327, and we'll save that. Now we should be able to call the do file work async with either Matt or Felicia. So we could come in here. We've got one with Matt, and we can copy that. And we can call it with Felicia. Now the problem is, if we do this await, what's going to happen? We're using that callback model, which means we'll do the one with Matt, then we'll wait here. After that's done, we'll do the work for the Felicia file. That's not really what we want. In this case, we actually want both of those things to go off and start. And when they're both done, we want to go on. So instead of a wait here, we can have a task. Remember, that function returns a task. Await is just a nice way for us to say, I know I'm getting back a task. I want to wait for that task. So we're going to do the same thing here. Now we're going to create our task variables. So we've got that information. And now, essentially, we want to be able to await both of those things. So we can say I want to await task.when all, and then I can pass in those two operations or those two tasks. Now, if we go look at task, we've used when all. You can also use wait all, which is more of a blocking call. We've got the await there. You've got the ability to run them. You've got a variety of different options for managing tasks. But for our purposes, we're just going to focus on this notion that we can get back a task from an async operation rather than awaiting it. And we can then manage those tasks by waiting for all of them. So I've got this code now. We're writing out with our simple thread async. We're going to have two different tasks for Matt and Felicia. And we're going to have, after they're done, this console write line work happening in the main thread. So let's move this up here and see what happens. We'll go ahead and run. So you can see we've got in our second part there, that second yellow line, the main thread ID, file access thread 1. And then notice we have employee read from file employee, and that's the Matt file. And then the next line is work happening in the main thread. So that shows us that these tasks are often running and they're happening asynchronously. So we're able to start those. They started running. We're still back in our main thread here doing our console write line. And then we wait for all of them. And we could then go on and do other code that applies once they're done. We've achieved our goal. We've created two different tasks. We've started them both. And we've been able to wait for both to finish. And in between, while they're running, we have other code that can be executing on our main thread. As you look at the output here, you may be wondering, why is it in the first example, when we created the thread and did start and join, we have a thread ID of 1, and then in the file access, we had a thread ID 7. But if I look down to the second part where we use the async, everything says thread ID 1. Well, that's the difference of how deep we're going and how much we're managing this. Note, when we created a thread, we literally created that thread, and everything in the do file work is running on that thread. That's why we see that different thread ID, because we very specifically created it. If you look here, remember, we're awaiting a method. We're awaiting that do file work async, and that starts processing. And while it does, it's still on the main thread. So our file access thread here, we haven't really created a thread for this to work on. It's when we get to line 73 and we do an async operation that under the covers, another thread will be created if needed, and we're not writing that out. So we don't see that that thread is being created in the background. Using tasks then gives you a little more control and allows you to have multiple pieces of work that you can then start and wait on in whatever fashion makes sense to you. If it's one of them completing, if it's all of them completing, before you move on that main thread. We've now seen two different ways to use the task model to do asynchronous work. If we want to use the await, we can do that inside an async method. So line 48, our simple thread async, is an async method. That means we can await things in there. Or the model we just used, where we can manage the tasks ourselves, and we can use the task then to wait for all of them to complete or for any of them to complete, for example. We also talked about exceptions earlier, and so I want to talk about those two together because when we move to this model where we manage the tasks, we can get different kinds of exceptions. So I'm going to change down here from awaiting this to using the wait all. And then we're going to change a couple things here to cause some errors. So I'm going to change the name here, and that means we're going to not find the right file. And then I'm going to come in and I'm going to remove that comma. So now that JSON file is invalid. So the code on line 54 should fail because the JSON exception is going to happen. And the code on line 55 is going to fail because we're not going to find that file. But because these are tasks and they're asynchronous, they're not going to fail right away. It's really this wait all on line 59 that's going to cause problems. So let's do a try, and we'll wrap the whole thing in the try. And then we're going to catch, and here I'm going to catch an aggregate exception. And this is something that the task-based asynchronous model uses to capture all the exceptions that happen inside that asynchronous work we do. So we'll go ahead and write out the message just for now, but we're also going to put a breakpoint here so we can see this exception. And the last thing I'm going to do is go out to our program and just comment out our simple thread. So we're only running this asynchronous one and we can see it in isolation. So again, we've got two tasks. Each should fail for different reasons. And we're doing a wait all here to wait for all of them to complete. So we'll debug that with F5 or by clicking here. You can see now we're in that aggregate exception. And if I go into that, the message is going to be a number of things. One or more errors occurred. But what's great about the aggregate exception is I can drill into it. I have inner exceptions, and you can see that I have the JSON exception. We go to the inner exceptions here. I've got a collection now of the actual exceptions with each of their stack traces. So now I can see here, this one is my JSON exception. If I go down to the other one, I'm going to see that's the could not find file in there. And we'll exit out of that. So we wrote that exception out. Now, one of the things you can do with this aggregate exception is you can handle particular exceptions. So if we look at the aggregate exception, we have, of course, those inner exceptions. We have the ability to flatten out all of these. So if you have a number of exceptions or multiple aggregate exceptions, you can flatten them out. But we also have this handle method, and that takes a method, essentially. We're going to talk about delegates in the next chapter, but for now, it takes something that's going to take in an exception and return a Boolean. So let's name this inner. That makes more sense. We're going to pass that in. And so I'm just going to say inner is JSON exception. Now notice I don't need to put a return there because it's just a single statement. What that means is if the exception, the inner exception here is a JSON exception, I'm returning true. That means I've handled it. But it also means I haven't handled the file-based exception. So let's go ahead and run this now. We still have the two different exceptions. You're going to see now when it comes out here, the aggregate exception got rethrown. So I go into the details. There's my exception again. The inner exceptions, now the count is 1. And if we look, we can see that is the could not find file exception. That's our IO exception. So we've handled the JSON exception, but since we didn't handle the other one, it continued to propagate up through the stack, and it's now getting caught essentially here at the program level. Just keep continuing, and we'll get back out to our code, and we'll see that gets thrown up there. When we use the await pattern, like we did before with the await and async, we don't worry about this as much because .NET handles for us the translation or the mapping of that exception onto the actual exception type. So if I were to await the do file work async for these two, then I would see that the actual exceptions are what I'm going to try and catch in my try catch. And in fact, that's a good thing for you to try. So we'll do a follow up, switch back to await the two method calls, and catch the appropriate exceptions. So you can give that a try, see what those exception types are if you await the do file work async on line 56 and 57, and you comment out the task wait all on 61, you're going to see slightly different behavior. But that aggregate exception is really helpful when you're managing those tasks and you're waiting for multiple things. And you have that handle operation so that you can say, some of these are okay, I've handled them, I've logged them, I've done whatever I need to do. And if you've handled all of them, great, that's a regular catch. If you don't handle all of them, if you return false for some reason, then you're going to get that exception propagated up. I'm going to go ahead and clean up our environment here a little bit. Just leave our program.cs. And we're going to comment this out because now we're going to start talking about delegates and events and expressions all kind of fit together. We start with this notion that I have a method. So I have this method called write hello, returns void, takes in a string, and then it's going to do something. A delegate, in simplest terms, is a pointer to a method or function. So I can declare delegate, del equals write hello. Now I actually don't want those parentheses that were put on there automatically for me because I'm pointing to that method. I'm not invoking that method right there. Now I have this delegate del variable that can invoke that method because it points to it. So I could do something like this. I could say dynamic invoke, and you'll notice the signature is that it takes in an array of objects, and they can all be null, and it returns a nullable object. We're just going to call that. And you'll notice because write hello takes a string, we should pass something in there. So I'm just going to pass in my name for right now. We've got a method. We've simply declared a pointer to it, and then we've said, I want to invoke that. So I'm going to Control F5 to run without debugging. You can see we ran our write hello method to write out hello Matt. I'm going to go ahead and go out to my library project here, and I'm going to add a class, call it delegate samples, and we'll make it public and static like the other samples. And now what I want to do is the other side of this. I want to be able to declare a delegate. I can actually have a type with a signature. So I can do public delegate. The return type is void. I'm going to give it a name. Let's just call it del for now. And what is the signature? Well, we could say name, could say input. We can call that whatever we want. Now notice there's no implementation here. This is just a declaration that says a delegate called del takes in a string and returns void. Well, now I can use that in some work or some function. So I could say public static void pass me work. And what I want then is a del as the parameter, and we'll call it work. What is work? Work now is a delegate, so a pointer to a function that takes a string and returns void. So I can call work. It's got the signature, and I can say delegates. That means I can now pass to this function my own function. I can use it as a callback, or I can use it as a completion. There are a number of different scenarios where you want to be able to pass a method or a method implementation into another method so that it can be invoked. So now if we go back to our program, we're going to use this delegate samples and call the pass me work. Delegate samples, pass me work, and we can pass in write hello just like that. So what's going to happen? Well, our write hello is a method that takes a string and it writes hello, whatever that string is. Our delegate samples over here is going to get past that. It's going to invoke it with the word delegates. So if we run, we should get our first one, which is hello Matt, and then we get hello delegates because we've invoked this write hello method and passed it delegates. This allows some great flexibility in being able to define and pass around these functions. And if you're writing a library or a class, you may need to do some work, but you may also need to offload or delegate some of that work back to the caller so that you can call back to the caller and have it apply some logic or do some work in the scope of this particular operation. Another case where we want to use delegates is when we want to raise events. And this is what's often referred to as a multicast delegate, meaning I'm going to be able to invoke a method once in my code, but it may then trigger or invoke many different delegates. So I'm going to come into my class and declare this event. So we're in a static class, so it needs to be static We use the keyword event. Then I need the delegate. What is the signature for this event? When I go and raise this event, or I call all these delegates, what is that signature? And here I've used my delegate that I've defined with a string input. Then I need a name for my event. So we'll just keep it simple here. Something happened. Now we have an event. What are we going to do with it? Well, we can invoke it or raise it. So I'm going to just paste this bit in here. I've got a method, do something. I'm going to write line. I'm about to do something. So we'll get some status there. And then very importantly, I'm going to make sure that event isn't null. That means that some class has registered for this event. It said, I want to have my delegate invoked when this event happens. And then I simply invoke that delegate. So I use the event name. The signature is going to be whatever the delegate was that I provided as the type for that. So you can see here, it's my del that takes a string. This gives us another way to let external classes or code get callbacks or get delegates invoked. But in this case, when I call something happened, it may be 1, 5, 10 different classes whose delegates will get invoked. So if we come back here, we'll see we need to go to our delegate samples. Something happened. Notice it's got a little lightning bolt there, it means it's an event. And so I can choose that, and then I can plus equal, saying I want to add a delegate to that. And in my case, it's my write hello that I've passed in. I'm saying, here's my delegate. I'm adding it to any other delegates that have been created for this. So when something happens, I want you to call that. And then if we use our delegate samples again, we can do something. Remember, that's the method that's actually going to invoke that event or those delegates. Then we'll go ahead and run that. So we've got our hello Matt and our hello delegates from before. And now we've got the I'm about to do something. Remember line 41, we called do something. That's the first line of code in there. And then we raised the event. We invoked our delegate. And so it says hello, because that's what our delegate does. And then the string that was passed to it, I did something. Again, we go back here. There's our write line. And then there is a listener. And now we say something happened with what we want that delegate to receive as a string input. Close that. Another example we can use, and I want to show you another thing about events. I used a very simple delegate there, but if we look at the console, we've been using it to write line. But you can see a cancel key press here. So we can say, I want to plus equal that, and we'll say something like on cancel without the parameters. That means we need a method called on cancel that matches that delegate. And the delegate for that is a console cancel event handler. So let's go down here and we'll add a static void on cancel. And a common pattern for event handlers is to have an object that's the sender, and then event arguments, console cancel event arguments passed in as well. So the sender can be null, can also be the class or the object that sent it if that's important to you. But the args are often typed in order to give you control over that event or have you react to that event in a certain way. So for a cancel event, notice in the args, we have a cancel property that's a Boolean. So I can actually indicate if I want to allow this to cancel or if I want it to continue. So we can set cancel equal to true like that. So I've registered the cancel. We're going to have all this other stuff happening. What I'm going to do is a for loop, and we'll keep 0 and we'll go out to say 1,000, 10,000. And we'll just have that print out that number. This is just so that something is happening here. And then I should probably tell us to hit Control plus C to cancel. So let's go ahead and put a breakpoint in here so we can see it. And let's debug that. But we're now setting up an event handler for the cancel. We're going to make sure our code is going to do something for a while, so it's cancelable. And then when we cancel, we should get this event firing our delegate. Control C. There it is. We've got our cancel. Notice cancel is set to false. By default, we're going to set it to true. And I'll hit F5 to continue. And because I said true, it's actually going to continue through here. Hit Control C again. I'm back to that. I'll do F10 to step. Come down in the immediate window and we'll say args.cancel equals false. So we can see that's actually false now. Now if I continue, you'll notice it's stopped. It's actually canceled. We're on our read line. And then it completes. It's a very common pattern for events to have the delegate be an event handler, which is essentially a delegate, but it follows a signature where you have the object sender and then some kind of event args class or derived class that provides information about the event. One last thing I'll mention here is that for events, you should clean up those handlers. So for example, when I came in here, this was my callback for that event. If I'm done listening for that event, I just needed to know about it once. In that case, then I would want to say delegate samples. And I've got that something happened. Now I'm going to do minus equals write hello. I'm removing that one handler, mine, from the list so it doesn't left out there dangling. I don't now have a pointer back to this method. So it's a good idea when you're done with those events for you to clean that up. I'll leave it to you to do the same thing down here with the on cancel, thinking about what's the scenario when you would want to remove the event handler or delegate. So that might be testing that args cancel. That might be depending on what you're setting it to. So in our case, we're setting it to true. We probably don't want to cancel the event handler because we might come back in here. We didn't actually cancel the process. We've gone ahead and cleaned up our program CS a little bit here. I had a lot of stuff there and it was getting a little out of sorts. I'm going to go ahead and comment all this out right now. So Control EC. I'm going to comment that all out just so we're not running everything. And then I'm going to go into my delegate samples. If we look at this delegate we declared, where we take a string input and return void, you might have thought to yourself, gosh, why do we have to define that? It's a method signature, it takes an input, and we have generics. We learned about generics earlier. Let's do something better. Instead of having to always define delegates that are going to essentially be method signatures with typed parameters, it'd be great if we had something like this. Action of T, or all the way from T1 to T16, you can have up to 16 generic parameters, is a built-in delegate for method that executes, has 1 to 16 type parameters, or actually 0 to 16 type parameters, and is going to not return anything. So simply by changing that to action of string, my pass me work should work now. I can actually get rid of my delegate definition. Now that's going to mess up my event. Can I change that to action of string? Sure, that's a delegate. That's all I need there. So we're back to my pass me work. Let's go back out here, go down to the bottom and we'll call it again. Delegate samples, pass me work. What do we need to pass? We need to pass that method again. So we could just pass our write hello. I'm going to have to go up and uncomment that, but it still works the exact same way. So Control EU, uncomment that. I'm going to go ahead and get rid of that event unregistration because we're not using the events right now. And let's change this to say actions in action and whatever that name is. Again, the functionality is the same, but actions are really going to help us reduce the need to declare our own delegates. So there we go, actions in action, delegates, because when we invoked pass me work, it invoked our delegate, passing in delegates. Actions then can have up to those 16 input parameters, but they don't return anything, whereas we might want to have a delegate that does return something. So we can do a static void, we'll say pass me logic this time. And now I want a func of t. So let's say I'm going to pass in a string and it's going to return an int. We'll call that worker. Now I can invoke that worker. So I can say int count equals worker, invoke. Notice it takes a string and it's going to return an int. So I'm just going to pass in hello world here. So some function that is going to be passed to me is going to give me a count based on that string. I don't really know what the logic is. I don't know if it's all the characters, if it's non-white space characters. I should know that. But for now, all I know is this method takes a string and returns an int. It might tell me how many times L happens in there. So then we can write out function returned, and then we'll put in the count. So what's missing now is a method that takes a string and returns an int. We've got a parameter of that type. We are using it in here, but we actually need to invoke and pass something in. So let's go back out here. So I have a static int calculate length. It'll take a string input, and we're going to return the length of input. Now, if input is null there, we could get an exception, but we'll return that length back out. And that means that we can now do delegate samples, pass me logic, and it wants that function. So we can say calculate length and pass that in. So now when we pass it work, we're passing it an action, a method that takes parameters but doesn't have a return value. And when we pass logic, we're passing in a function that does have a return value. So you can see when we run that action, it again says actions in action. When we invoke and pass the function, it counted up the letters, and so the function returned 11. Inside of our method here, we were able to call back out to the caller or invoke the function passed and then use the results of that inside of our application logic. So action and function are really just helpers for delegates so that you don't have to go out and define them like we did on line 13 over and over again with different names and different names of parameters. They're all essentially the same. Methods with typed parameters. So we get generic delegates to simplify that. Action and func help us not have to write the delegate declarations. By the same token, lambda expressions are going to help us not have to write methods. So for those cases where really the implementation of that delegate is very focused, we don't need a standalone method for it. We want to be able to have a way to write a method without having to fully declare it or write that logic. And these expressions come in two forms. So I'm just going to call this var t, and I'm going to have a parameter list. So string s, I'm going to use this expression to point to the lambda. So now I've defined the parameters on the left. Now the implementation comes on the right. A simple expression would look like this, where I would now write console write line and pass the s. I'm not returning anything. I'm not doing anything there. I'm simply writing out. I've got a statement or an expression there. And that means that I should be able to invoke that by doing something like this. Hello world. Because that expression is a method. Now, another way we can write those expressions is to have the full statement there. So I can use this. I can say I'm taking in a string s, and then I'm going to use my lambda expression symbol here, and then I can use curly braces. And I can then have multiple statements in here. So I could write out the s. I could also then return s.length. So I have a full set of statements there. This is essentially a method declaration, but I've simplified it in this particular case. Of note, if we were going to use this expression model, where we just have the single expression, let's say I'm going to have this copy paste, I'm going to call this T2, and instead of writing it out, what I want to do is return the length like I did below. Because it's an expression, I don't actually need to use the return keyword. I simply write s.length. And that's now understood to be a value that's returned. That's providing a value. The expression evaluates to some value, and that then is what would get returned to T2. Those are the key things to understand about basics of the Lambda expressions. So on line 70 and 71, you can see we have our parameter list. In this case, we're defining the type, string. Then we've got the operator that indicates that we're going to have an expression. And in both these cases, line 70 and 71, we simply have an expression. First one doesn't return anything, so it's going to simply write that out. The second one does evaluate to a value. So this is a case where we're passing in a string and we're going to return that length. And down on line 75 through 77, you can see the statement based, where maybe when we have this method, an anonymous method essentially with our Lambda expression, we don't just have one single expression to evaluate. We've got multiple things to do. We can use the curly braces to encapsulate everything to the right of the operator and make that essentially a method body. And again, there we can use the return if we need to provide a value back when those operations are done. Since Lambda expressions are essentially anonymous methods, we can use them when we talk about delegates. So we think about our pass me work here where we passed write hello. What does write hello do? Well, it takes a string and it does something. So that means we could, instead of passing a method there, pass an expression. We could say hello expression, and then we could pass in whatever that s is that comes in. And just drop this down onto another line. Got some extra punctuation at the end there, but not that much. So we have pass me work, and instead of passing a pointer to a method, instead of passing that write hello, I can just pass an expression. It says, here's your delegate. It matches a signature because it takes a string and it does something in there. Notice that I don't have to say string s in parentheses because pass me work has already defined that signature. If we go back and look at that method, you'll remember that it takes an action of string. So it's looking for a delegate that takes a string or a method that takes a string. We've provided one here, and we don't have to then also specify over here the string s. That's already implied by that signature that's provided. Likewise, for the calculate length, if you think about it, we could just take this expression we had down here, copy that, come up and paste it here. Again, we have the string, but we don't have to put that there. We can get rid of it because we know that this pass me logic is expecting that. Get rid of that one extra semicolon there. And now when we've called pass me logic, again, we've given it an expression. We didn't have to have a separate method defined for that. We can define the method inline here using the expressions. So we can get rid of calculate length. Just comment that out. We'll leave these other ones down here as well. We're going to write those out. When we run this, we should see that pass me work is going to run and call hello expressions with the s, and pass me logic then is going to write out whatever string gets passed to it, and it's going to return the length, which remember we use over here to get a count. So on line 23, we're going to be able to see that count come out because we've invoked that expression from this method. So we've got our hello expressions delegates. That's the pass me work getting invoked there, calling back into our Lambda expression now with the word delegates. Then we have our hello world. That's what was called or passed into that function. When we call worker here, we're calling that expression we defined. And we first do a write line. And then the function says what it returned here on line 23. So we get all of that logic simply embedded, those anonymous methods being able to be passed as delegates because they match the signature. Now, if I did something like this, well, now I no longer match the signature. Now I have a method that takes 2 parameters, but pass me logic is expecting a method that takes 1 parameter. So our expression is going to have to match that signature. And if I look here, pass me logic, I can see that it takes a func of string int. And so I know I need to pass a string. And the second one is going to be the return type because it's not an action, it's a func. We've seen this in use. If we go back and look at our thread samples, you remember when we did our aggregate exception on line 65 here, that aggregate exception had a method called handle, and it takes a function or a func that takes in an exception and returns a bool. So this was a Lambda expression that we passed in. It takes in an exception. We named it inner. And then on the right side of the operator, we're able to use that inner, which is of type exception, in our logic. And of course, this Lambda expression just has the expression. Simply inner is JSON exception. That results in a true or false value that gets returned. We could have also done a statement-based expression. We could have done a number of things like write out the message from the inner one. Then we could come down and return inner is JSON exception because now we are inside that statement and we do need the return statement. We didn't go over it while we were here because we hadn't touched on it yet. I wanted to loop back here and show you this in use with a part of the framework so you can see how you can use those Lambda expressions or those anonymous methods. I didn't have to go define a whole method here that matched the signature and figure all that out because this logic is really only going to happen in this catch block. I don't need a whole separate method for it. Now that you've seen expressions and seen them used in a couple different ways, you may be thinking back to earlier in this class or other classes, other examples where you've seen something similar. For example, let's go to our employee class. We can use expressions when we declare methods. So I could say public override toString, and it wants to give me this implementation, but I'm going to come back out and I'm going to use that operator for my Lambda expression. And then I can just do some string interpolation. So I can do first name, and then maybe I want to do an underscore, and then I'll do last name, and I'll put a semicolon at the end there. And that now is a method body. So I've provided an expression instead of the normal method for defining a method in order to provide that implementation. Likewise, we can use that on properties. So maybe I've got a private string f name that we'll use for our first name. So if I come down here for my get, for example, I can just use the Lambda operator. I know that this is going to return a string, so I can just put f name. That's what that's going to return. I could use set, or I can change this to init. I can use that, and now I can say f name equals value because I know that's what that operation signature for the property looks like. It takes in a value of that type, and we want to set it into that variable. You can use it for properties, you can use it for methods, and you could use it for constructors. With the caveat being that the constructor has to take a single parameter so you can set it in a expression. So we'll do a follow-up here. You create a constructor to initialize the first name. You'll want to do that using that lambda expression to set either the fname field, or you can go through the first name property based on a parameter. I want to talk about one of my favorite parts of C#, and that's extension methods. But first, let's talk about why we need them. So I'm going to close up a couple of things here just to clean things up, get us back to our program. And I'm going to add a new class to our library project. So we'll add a class. I'm going to call that string extensions. I'm going to make it public and static, just like we have the other ones, so we can get at the methods easily. And I'm going to come up here and just add to the namespace. So I'm going to add extensions on here. And I'll talk about why a little bit later, but the key thing to remember is our string extensions class is in the Essentials2 library extensions namespace. I often want to work with a string and grab different bits of it. A lot of the code where I work on client applications, I need to be able to parse out specific pieces. And the string class doesn't have a write method to grab the rightmost characters. So I might do something like this, string input, and I probably want to make that static, just like the class, and say I've got the write. And so if string dot is null or empty input, then we're just going to return string dot empty. So we want to make sure we handle those cases. Otherwise, let's say we want the right X number. So we want to add on here maybe an int for number of characters. How many characters do we want from the right end of the string? And now I can go in, I can do input substring, and then I can provide a start index. So I can take the length of the input minus the number of characters. So length minus numchars. That gives me my starting point, and I want to return that. Now we could put some additional error checking around here. All right, we might want to error check that the length is greater than the number of characters. That would be a good idea. But you get the point. Our implementation simply allows me to get the right n or x number of characters from this input. And so if I go to my program, we'll comment out the code that we had here back in our program CS just to clean things up. We'll go down to the bottom and we'll add some additional code. So that's in our Essentials2 library extensions. Extensions. String extensions. Well, we can choose write. And now let's say I want to pass in something like this, write 4, and then I want the 4 characters. So var write equals, we'll grab those. And then we can write out the write. Well, let's run that. We'll see if we've got all our logic correct here. We don't have any errors. Great. I've now got that functionality to grab the rightmost n number of characters from a string. But notice how I had to do this. I've now got to call the write method on my string extensions class. What I would love is if I had a string like this, string s equal write 4, then I could do s dot write. I have a pad write. That's not what I want. I want to be able to grab and maybe just do those 4 characters. So I want to be able to call something like that. Keeps correcting it to pad write because that's the method that exists. This doesn't currently exist. And I don't own the string class. That's part of the .NET framework. I can't go in and change the string class. Wouldn't be a good idea based on how many things depend on it. But I don't have the control to do that. And yet I really want this to appear as a function of the string. And that is where extension methods come in. And we'll see how to implement them next. Now I want to go change that method in my string extensions to be an extension method. And it couldn't be easier. I'm going to go to the method. I'm going to type this in front of the type string for that input. And now this is an extension method. And it extends whatever that first type is. So it extends string in this case because that's the first parameter. Importantly, when I'm in here, notice that as I get the input, I don't have access to any additional functionality of the string class than I would in my normal method or operation that I had here. I have all of the same access and I have all the same methods and properties available to me. So I'm not getting internal access. I'm not changing the way that I can work with string. I'm simply changing how this method is going to be accessed on the class. So now, same idea. We're going to get that input. We're going to check if it's empty. And then we're going to get that substring based on the length minus the number of characters. And this may not seem all that exciting or important right now that we're able to create this method because we don't get that internal access, but we are now adding functionality to the string class for consumers. It will look like a method on the string and it will simplify the programming model. Now that we've got our extension method, we can go out and use it. So I can come back out here, uncomment this, and voila, that should work. But I'm getting that red squiggly. It doesn't understand that that write method is part of the string. And I'm showing you this because it's important and you're probably going to run into it. I can't tell you how many times I've found a method, the documentation, or I've worked with a developer who's seen an example and they're looking at it and they're trying to understand it, but it just doesn't work for them because it doesn't know about this method. And this will go back to C# Essentials Part 1 and the notion of namespaces. You remember I put that type in a slightly longer namespace with the extension's name on it. I told you it would make sense later, and hopefully now it does. I'm going to save that, go back down to the end, and now it understands the write method. That static class that has our extension method in it has to be in scope, has to be in namespace scope. And sometimes when people write libraries or even in the framework, those extension methods are in a slightly different namespace, or they may just be in a namespace that you haven't put in scope with a using statement. So we could change this to something like write 5s, just because that makes it 5 characters and will be slightly different. And we can write this out now because that's going to return the write 5 characters. So we should see 4 and then 5s if we run this. And there we go. So now we've achieved what I wanted on line 91. I can now have a string variable and it has a method on it called write that will give me the rightmost characters. And I've encapsulated that logic in one place. So now in my string extensions, if there's a problem with my logic, if I need to add additional error checking, I can do it in one place. And I know that it will get used in all the places where my library or my class is getting used. And I've fixed it for all those places. And I'm not duplicating the same logic of checking for null, of checking length, of grabbing that substring based on the length minus the number of characters. There are a number of different places in the framework where you're going to see extension methods and you're going to see how they extend different classes in the framework, but you can also use them to extend those classes yourself. You can create these utility methods that you can use throughout your projects. One of the most common places you'll find and use extension methods is on collections. We're going to look at, in the next chapter, language integrated query, and it's going to take advantage of these extension methods extensively. If I just take a look at a list of string here, I've got all of these items. I can look at names dot, and because the namespace is in scope, I get all sorts of different options here. I see this as queryable and as queryable of t. I get an average. I get the ability to cast. I get some element at or distinct. So we're starting to see some things around selecting different items here. First, we can do, well, there's a new one with C#10 called min by, where we can get a minimum. So Let's do that. Let's do min by. What am I going to get? I'm going to get a string, and it wants a function of type string. So we're going to go in, we're going to pass it that s. We'll use our lambda, give it s.length. So what's that going to be? Our shortest equal shortest name, and then we can do shortest. So what that's doing, we look at our expression we passed in. We're saying if you give me the string, I'm going to return the length, and then we're going to do a min by. So give me a string from this list. I want to find the minimum, and I want to use this function to decide what the value is. So let's go ahead and comment out these other steps up here. And we'll run that with our collection. We can see that the shortest name is Z. Of course, it's only 2 letters. So that's one example. So you'll see that these extension methods aren't on the collection class itself. List of T doesn't have these. They extend it. And I can do things like order by. And again, I'm going to pass the string in. And we'll use that string.length just because it's a simple example. And what's that going to give us? Well, the order by is going to return another collection of those strings. So we'll call that ordered names. And then we can just do a for each name in ordered names. And we can write out the name. So if we've ordered those by the length, we should see those come out in order based on how short or long the names are. We've got the shortest name, and then you can see, in fact, we did go from shortest to longest there. Those are just a few examples of some of the extension methods, and we're going to see in the next chapter when we talk about language integrated query, how we can use those to work with collections and work with a variety of different sources of information to query for values we want, for items we want. In the previous 2 chapters, we've looked at expressions and extension methods. And while they both have great usability and provide excellent features in C# on their own, they're also part of a foundation of language integrated query, or LINQ. So let's take a look. If we comment out our names here, which is just a simple collection of strings, let's add a collection of some types. We've got our employee type here that we've used. With the extension methods that we looked at for collections, we can do a number of different things. For example, we could take a look at our employees, and I could say I want to do employees, and I can add a where statement on there, and now we're going to have an expression. So we've got a extension method with the where method, and we have an expression. So now we need our expression with our input, and we're saying where, and now I'm going to return a true or false. So I can look at this and say e.id is greater than 2. And that's going to return, if we look by mousing over, see it's going to return what's called an IEnumerable of employee. That's one of our collection interfaces that we can enumerate over. If we do that, we have our filtered employees. So we're going to have some subset of that comes back out. So let's go ahead and we'll just comment out the last bit here. And now because it's an enumerable, we can iterate over it. Got our filtered employees. And now we could write out, because that's an employee, we've got all that information, but let's just write out the first name. If we look at the IDs, then we should see 3 different employees that get returned. Sure enough, we see Pinal, Amanda, and G come back when we have the ID greater than 2, so they all fit that clause. And this is great, and because these extension methods return an IEnumerable, we can actually chain things together. So if I do a dot here, I'm going to see a lot of those same extension methods come back. So I have the where, but maybe I don't need the whole object. I don't need everything in there. I can use a select And now I can do ES for eSelect as my parameter maybe. I can do ES dot first name. And now if we look, we're getting a IEnumerable of string. So we're really just getting back to a collection of strings. But we also learned in C# Essentials Part 1 about anonymous types. So I could say I want to return a new, say first name equals. Now I'm just using the curly braces here, and last name equals last name. We'll add the closing curly brace. So we've now returned an anonymous type that has a first name and a last name. So we've stripped off the ID now from our employees, but we've already filtered them. So if we look at filtered employees, it's now an IEnumerable of that anonymous type. It should still have a first name and a last name. So if we run that, we really shouldn't see any difference. Still able to use the where extension and only return those three. And then I'm selecting or now projecting those results into an anonymous type. And all of this is great. But what you're starting to notice probably is it's getting a little messy. We've got these extension methods chained together, lots of expressions together. And so the extension methods and the expressions are getting us some functionality. But when we talk about language integrated query, we really want the querying to be integrated into the C# language. Let's take a look at that next. Looking at this example, we can actually rewrite this in a slightly different way. Let's do a var, we'll just say f employees equal. Now I can use from, I can say emp in employees. So I'm now using some integrated query language. You can see that from and in here are keywords. I can now say where emp, and we can do the same thing we did before. ID is greater than 2. Select, oops, I've got to properly case the ID there. Now we could do the same thing. We can select a new object. In fact, we could just copy and paste this. So now we can simply change this to f employees. We should see the same results. If you've done any querying of databases, for example, or other systems, a lot of these keywords, a lot of this structure is very similar. It's slightly different from, say, a SQL query where you'd start with the select first, then the from and the where, but it's the same kind of idea. So we set up that query context of saying, what am I querying against? Well, the employees collection, and I'm going to represent each item with an emp variable. That's like the input to our expressions. So when I say where emp.id is greater than 2, you can see how that maps onto the where extension method up above, where I had an input into my expression, and I then created the expression that returned a true or false. We need to fix up our expression parameter names there for this so that it works. We can still have the filtered employees, but we're going to walk through the f employees as we execute that. You'll see we get the same output that we got before, but we have much cleaner syntax for writing the query here. Let's go ahead and set a breakpoint here, and we'll try this with the debugger on. There we go, and we'll just hit F10. We'll step over our debug spot here, or you can use the toolbar up here. And now if I mouse over F employees, or if we look at it down here in our locals window, you can see that the type is now system LINQ enumerable where select list iterator. It's a much longer and internal type name. And if we expand that, you'll see that current is null. And if you look at the results view, it says that expanding that will enumerate the IEnumerable. What that means is at this point, if employees hasn't been iterated through. Of course, then we're going to do that here. And that will become important as we talk later about other places where we can apply this language integrated query to query against different sources. So this is a fantastic way to work with collections of objects, be able to manipulate them to get the results that you need for your business requirements. And it's all integrated into C#. So this is all understood under the covers. The where, the select, all of that is really getting converted into those extension methods that we saw back on line 103, but it's a much better way to write these queries in your C# language. We've got a basic query here with some filtering with our where clause and our ability to select. We're selecting an anonymous type or projection, but we could also just select emp if we wanted to, just like that. So we can select the object itself. We don't have to do the projection. Get these cleaned back up. Now we can also add to this. So maybe we want the emp ID to also be less than 5. So now if we look at our employees up top there, greater than 2 and less than 5, we should really just see Pinal and Amanda. Could run that quick and confirm. Yep, that's what we get. We could also order this. So we could say order by, we could do emp ID descending. So now we're still filtering. We should still just get Pinal and Amanda, but because we're ordering by ID descending, Amanda should come first. In fact, if we run that, that's what we see. Another thing you can do is combine this kind of syntax with extension methods if you need to, because not everything is integrated into the query. So if I wrap this whole statement in the parentheses, that gives me the item, and then I could do something like this. I could say I want to skip one item, and then I want to take 3 items. Skip is going to skip over the first item in the collection. Take is going to identify a number of items we want to take out of the collection. The where statement was filtering based on some criteria. It was looking at the employee objects and returning a Boolean value. This is simply looking at them in order, skipping over some, and then grabbing a certain number of those. So we're going to order by the employee ID descending. We're going to skip over the first one and take 3. So if you look at the top there, get your guesses lined up as to what you think this should be. And we get Amanda, Pinal, and Felicia because we've ordered it descending, and then we've skipped over Z. We've taken only 3, so we get Amanda, Pinal, and Felicia. Now there's a lot more complex queries that you can write. You can do joins, so you can be querying from multiple collections or multiple sources. You can use grouping to get values that are grouped together and that projection. I'm just showing you a sampling of what the language integrated query can provide in terms of giving you this quick, easy way to query against collections in order to get out just what you need. I've found that I tend to use this with collections more than even some of the other sources that we'll see in the next clip. We've used LINQ to work with these collections of objects, and that's great. There are a number of other places where you're going to query data usually. So when you're working with a database, you're probably going to use Entity Framework or another library that helps you access that. But those tend to use collections, so the syntax and things don't look a lot differently. I will say one thing about them, which is in your expressions, you may run into some problems where certain things that you would normally type in here don't work. So for example, when we're working with our order by, we're just simply saying employee ID. If we tried to do something like employee ID to string, it wouldn't necessarily work. And the reason is that there's 2 different ways LINQ expressions can be interpreted. And one, when we're working with objects here, we create these expressions, they get executed in C#. Another is to take this LINQ statement, everything on line 106 to line 109, and make an expression tree But then a provider might translate that into something that SQL Server or a database server can understand. So you can't have, for example, method calls in here that wouldn't be understood on the server. But all that said, another interesting place is if you're working with XML, for example. And I want to show you this primarily because it does show the flexibility, but it also shows how things are a little bit different depending on what kinds of data you're working with. So if we say something like var x employees equals, and then I'm going to use something called x element, and that's not going to be in scope. I need to add the namespace. So I'll do a control period, and I'm going to use system XML link. Now that's going to put, as we know, the X element class, but also maybe extension methods and other things into scope. So now I can load, and I'm going to load just like we did with our JSON files. I'm going to load an employees.xml. Put a semicolon there. Well, what the heck is that? I've added this into our project files. So you'll want to look in the begin folder. You'll see that I've added the employees.xml there under the LinkedIn Essentials 2 project. And at the top, we have an employees element. And then underneath it, we have repeating employee elements. And this is going to look familiar because it's just like our objects we had, just so we can see the context here of XML. Each employee has a first name element, a last name element, and an ID element. Otherwise, this is the same data we were working with before. But we'll see now how this looks a little bit different. So if we want to do our expression, let's say something like xemp_link equals, and now we can do our from xemployee in xemployees, but that's not really going to give us what we want, because if we look at xemployees, that is an X element, a nullable X element. And we need a collection, or we need a set of items that we can query over. So I'm going to use .descendants, if I can spell it right, and that will allow us to pass in a string and say, well, what name do these descendants have? Employee. So when I load it, the top level X element is going to be that employees. Now I'm saying, get me all the employee elements underneath that, and that's what I'm querying against. And I could use the where. So I might want to do something like xemp. Notice I have name, value, node type. Those are the suggestions coming up on the top there. What I'm not going to find if I go down through this list is I'm not going to find first name and last name, because this isn't an object, it is XML. And so it doesn't necessarily know the structure. But I can say I want an element ID, and I want to be able to do what I did before and say I want that to be greater than 2. Now, when I get that element, it's a string. Everything in that file is a string, but built into the link to XML is the notion that an element can be easily cast to different types. I happen to know that element's an int, and so I can cast it to an int, and now I can compare it to that 2. Now this is where, again, we might want to use our projection to project a new object, because what we don't want is a bunch of XML. We want to get this mapped into or projected into some objects. So I can do first name equals, and then I can do xemp element, and I can do first name, and I can do last name equals xemp element last name. Now those are both strings, so I don't need to do any casting or anything here. Those are going to come back as strings and be assumed to be strings when they come back. And then we can do something like before. I'm just going to paste in here a for each. So we'll iterate over that collection now of those anonymous types coming back, and we can write out the first name value and the last name value. Now, why is that happening? Why do I need that value there? Let's run through it and we'll take a look. Notice I've got this first name, but if you look at it, it's actually the XML. So when I got the element and I got it back as a string, it gave me the whole thing. And that's not really what I wanted, so I used the value here. Now we know how we could clean this up by simply coming up here and using value. And now what we're going to get is the actual value on there. So we can take that off of here because it no longer makes sense. The objects we get back are simply going to be strings. Now we'll run that. We should get that same output. Now we get the first name and last name. We still see those first 3 lines from our previous example, but then our next 3. So we've done the filtering, we've done the projection across that XML document. So it's not quite as clean as what we were doing with objects, because with objects, we know the types, we know the different properties and what their data types are. The XML, it's not quite as easy, but with that implicit casting of the element that we can do, with the ability to get the descendants or query down in there, you can really work with XML in a much simpler way as you're trying to query through it in your C# code. That's one example. As I said, you can use LINQ with Entity Framework. You can use LINQ with anything really that creates those objects, but there are special cases like Entity Framework where it can translate your LINQ expressions into something that an external provider like a database can understand to actually execute the query. Hopefully that gets you started with LINQ in a number of different scenarios within C#, and there's a lot more that you can learn to dig into language integrated query. Thank you so much for joining me in C# Essential Training 2. I hope you've enjoyed the learning journey and that you're excited about the applications you can write with C#. As you look to the next steps, there's some additional C# training you could take. We really touched on LINQ at the very end, or language integrated query, but there's so much more you can do with it, and there's more complex operations and grouping that you can do as well. So if that's something you think you're going to use, I would recommend you go out and dive a little deeper with some of the LINQ training. Asynchronous programming is another piece where we touched on the basics of the async await model, of tasks. But again, if you're getting into multi-threaded programming, you'll want to dig deeper into some additional courses on asynchronous programming with C#, so you really grasp the fundamentals underneath that. Additionally, just like I said at the end of C# Essentials 1, other C# language features that you can look into, and then other frameworks. So Entity Framework is a very common framework for people to use for data access to all sorts of database systems. ASP.NET is a framework for building web applications. You have Blazor for building client applications using web technologies like HTML and cascading style sheets, but C# instead of JavaScript. You have Xamarin and .NET MAUI coming out soon, all for building cross-platform applications, especially mobile applications for iOS, Android, and Windows and Mac. And you have Windows Presentation Foundation and other UI frameworks if you're specifically targeting Windows. So depending on the kinds of applications you want to build, any of these last 4 may be a good place for you to move next with your C#. And if you're going to be accessing databases in any of those kinds of applications, Entity Framework is Microsoft's offering in that space that you'll want to take a look at. Now, other than watch courses, the main thing I can recommend is that you go build something you're excited about. When you set up some requirements for an application and what it needs to do, and then you set out to achieve that with a programming language, I found that's the best way to learn the language and to learn how to achieve the tasks that you're going to need in real programming projects. Again, thanks so much for joining me in C# Essentials 2. I hope you've got a lot out of it and have a great time building applications with C#.